This is a follow-up discussion. I don't remember the exact date. You can find out from the video on YouTube probably, but a few years ago at this point, I had a conversation with Casey, and it was just sort of, it was this topic that had been bubbling around in the background for a while, like parsing programming languages had bothered you, like the way it's discussed or whatever.
Mm-hmm.
We go into much more detail in the talk. And I had done it a bunch. And then especially for this programming language I'm working on now, I had to do a much more thorough and serious job than ever because there's just way more features in the language and there's more weird cases that come up. And so, the main gist of that talk back then was like, look, this thing that they call recursive descent parsing, which is a very technical term that what it actually means is just write code the way you normally would for any other program, right? And
Yeah.
don't do any of the crazy shit that they teach you in college. Is the right way to write a parser, like unambiguously, and it's much simpler, and you get better error messages and all that. Anyone who's interested in that can go watch that video. Now, one of the topics that came up, toward the middle or toward the end was the operator precedence topic, right?
Mm-hmm.
And you were like, what do you do for operator precedence? And what I said at the time was, well, I do what I think is probably the second best thing, which is I do this tree rewriting, which is just, to summarize it very briefly, we'll go into what this precedence problem is in a second, too, if you don't understand it. It was just like, look, anytime you make a node, if there's a precedence problem, you can detect it by only looking at one layer of the thing, because by induction, everything else is correct. So if you just rewrite your tree with some random function, then you're fine. and you don't have to think about any computer sciencey thing, right? And that was a totally reasonable way to do it. It certainly worked for 9 or something like that years, depending on how you count. I mean, the compiler was a side project at first, but a long time. Beta shipped to hundreds of happy beta users using it. But then, Christmas time and New Year's is often a very productive programming time for me because, or game design time, honestly, but programming's easier when you're overworked. So, I did a bunch of stuff, but then sort of at the end of my New Year's time, I was like, hey, let me, I think something initiated this. Like I wanted to change some feature in the thing. And I was like, oh, I have to go deal with this parser thing. And it felt a little bit annoying. So I said, hey, let me just go back and see what I can do about the precedent situation. Can I do it what I said was the first best way? And can I do it as cleanly as possible? And can I really understand it clearly? Because part of the problem is, part of the reason I didn't do it that way in the first place, way back when I started the compiler, was I would go read some of these references and they're like really hard to understand. And, I don't exactly see how this relates to what I'm really trying to do and all this. And we'll go through some of those references. But the point being, last week, I think it was Saturday, 1 week ago today, I just rewrote the way precedence works in the parser, and got rid of all the tree rewriting, and it works great. And I did that for the programming language. It's not a toy language. It's a C++ competitor language with a pretty complex grammar. And so I just want to not even talk through the method so much, because the method is, I mean, it's so simple, it's unbelievable that it's even been a problem for decades, right? That's really the point that I want to get to, is it's so simple, it's crazy. And if anybody had ever just sat down and said, look, here's the thing. And in fact, there are a couple of references that kind of do that, and I'll go to those, but the problem is they're
Yeah.
hard to find on the modern internet. Like,
Yeah, I would say that like there's been a couple things that people have pointed me to. I think actually after the discussion that we had, where they're
yeah,
like, it's actually really simple. Like here's two examples that like I wrote up for you. And it's like 5 lines of code or whatever, right?
yeah,
And I'm like, oh, and you would never know that if like primarily what someone handed you was the Dragon book, right?
Yeah.
You would have no idea that anyone had ever figured that out, because you would have assumed, well, surely they would rewrite this part of the book if you could do it, but they
In
don't.
fact,
And so it's very misleading to people who are getting into this, because the things that they will find end up being like really obfuscating for some reason.
yeah, since you're on this, we'll go back in a second and explain what this is for people who are lost, right? But, so the Dragon Book was 1986. I went back and looked, right? And
Yeah.
that's sort of based on this Green Dragon Book, which was an earlier thing from 1977, right?
There's a Green Dragon Book?
Yeah, we actually had a few copies of it at Berkeley too. It was what you would buy at the used university bookstore
Okay.
if you couldn't get the other one.
Okay.
So the sort of the paper that everyone cites that lays out how to do this is this top-down operator precedence paper from 1973, which predates the Dragon Book by 13 years. Okay.
That's amazing.
And even the Green Dragon Book by a few years. But actually, that's actually the same thing as something that Dijkstra did in a paper called An Algol 60 Translator for the X1, right? Which, how would you ever think about reading that paper from the title, right?
Right.
But it's obfuscated because it's this thing called shunting yard algorithm,
Right,
which is
yeah.
about stack manipulation to put things in this fourth, like, thing,
Yes.
right? Which doesn't really look like very much like what you want to do if you're parsing a programming language. However, it's the same. It's like understanding what order the operations need to occur in, and then making the correct output, right? And the making the correct output step is different, but the understanding it is the same. I didn't really try to read that paper though, too, because the more you go back in time, the harder computer science publications are to read, because everything was different and you don't have context, and a lot of terms mean different things now than they meant then, and stuff. But also, honestly, what happened with this was I also just have very little patience now for trying to read things. So if I start trying to read a few references and there's this thing that happens on the internet where there's a miasma of stuff and you start to get lost and you're like, okay, this person is saying it's easy, but maybe they're a bozo. Maybe they're not a bozo, right? I don't know. And the main way that I know how to know if someone's a bozo is to just go figure it out. And then I have a basis on which to judge, right?
Yes, I've noticed that. I tried to send you the LP FIFO paper, and you were like, I don't know, they don't explain the algorithm or something, and you didn't read it. And I'm like, no, it's a good paper.
I didn't like that paper. Okay.
It's a good paper.
Anyway, so to provide a little context for people who aren't into parsers about what exactly the problem is. Again, we cover this also, I think, in the previous video, so I'm going to go through it really fast. But one of the things about compilers and parsing the input text that I'm never probably going to argue with is this token abstraction, and we're going to assume it here. So you get raw text in a file coming in, and you have some part of your program that breaks that into slightly higher level things that are easier to think about and manipulate. So like, is something the name of a variable, or is something a number, or is it like a string literal or whatever? That happens before what we're talking about. So you have something that reads characters one at a time and breaks it into a stream of those. Now that's not actually strictly necessary to do. I've never done it any other way, but I'm just not going to argue with it here. I have no experience doing something else than that. Probably people in the early days of computers did do something else than that. So then what a parser looks like. So here's just a simple function for like parsing a binary operator. By the way, there's a lot of little code snippets in here. I just picked this is a pseudocode that is kind of like C, but with less punctuation. That's all I'm doing. So nothing special. So there's a function, like if you want to parse a binary operator without recursion or anything, just like A plus B, something simple like that. You call like parse leaf, which gives you this thing that's like, maybe it's a number, maybe it's an identifier. And so you could get anything. You could get A plus B, you could get 3 plus B, right? You could get 7 times hello, which in a reasonable programming language is going to be an error, but in some is not, right?
You're right.
So, So there's this fundamental layering of functions where you say, I want a leaf, and then I'm going to look at what the operator is. So here for parse leaf, I would parse this 3, and then the input is like plus b. And I say, what's the operator? And it's like, oh, it's plus. So we eat the plus. And then we parse the next leaf, which is b. And then we make a binary. Actually, so here my binary is a plus b. So, then we make a little binary tree. And what this is a representation of, it's like a node with a left pointer and a right pointer that could point at maybe other binary operators, even though this code can't generate that. Here it's just pointing at 2 leaves, right? A plus b, right? Now, of course, if you want to parse more than a plus b, the typical thing you do in a parser is you make this effectively recursive, whether the code's actually recursive or not, right? It needs to be able to, you need to be able to refer to other binary nodes and stuff, right? I'm not sure why I did this extra step here. This is just a version of parse expression that could return either a leaf or a binary operator based on what the next token is, right? This is a very typical thing to do. So again, if you say parse leaf, you get a.
Maybe just because you were trying to show like, okay, so if we want to do more than one expression, this is how we do it. Like
yeah,
more than one
well, that's what I'm trying to get to down here.
Yeah.
I wrote this like 5 days ago,
Okay.
so whatever. I don't totally remember. But so if you have a longer thing like a plus b plus c plus d, right? Then this can be recursive. And here it actually is recursive. In fact, like it calls itself. But if you don't like recursion, you can always convert a recursive function to a loop. It just might get really messy depending on what's going on. Anyway, so if it's recursive, you could say, let's parse a leaf, which here will be a, right? You can get the next token, that'll be plus. And then if that's a binary operator, which in this case it is, we call parse expression again, which will take this as input, right? And then that'll call parse expression again to take that as input. And that'll call parse expression again, which will take just D as input, which will return you a D. And then you make binary operators going on the way up. I actually skipped that step here. So the final tree you get out of this is this thing, right? A on the left, a root node, right? A on the left, and then B on the left of the child, and then this CD binary tree. And so all the leaves are in there. You can use your favorite computer science way of navigating this tree however you want. Now, it's worth pointing out, why is this a tree? Like what does the tree do? Well, okay, before we say that, let's just go, the point that I was making about talking through the recursion here is just that the first thing actually constructed is sort of this D leaf. And then you come back up the recursion. And now that you know what was on the right-hand side, now you have a CD, right? Now you have a BCD. Now you have an ABCD. Okay. This is the tree structure that is naturally created by doing this simple dumb thing, right? It's this right-leaning tree. If you have a longer and longer expression, it'll just keep going. You like extend this ladder to the right. Okay.
This may be out of scope for this discussion, but I might also ask the question at this point for clarity.
Mm-hmm.
If one were naively to look at that explanation and hasn't worked on parsers before, one might have the question, why recurse down to D and then work back up the program stack to construct plus C plus B plus A? Why not just put A in when you encounter it, then create the plus node, and then create the B, and so on? Like what is the value of using recursion at all?
Yes. Well, the answer in this exact case, for as far as we've gone, is that it's an arbitrary choice. You can do it the way that you said. And in fact, we will do it that way in a little bit.
Okay, never mind. Sorry to jump ahead.
No. It makes sense because it's so, basically if you went to school at Berkeley like I did, they love recursion and they drill it into you. And so it's the way that you would do things, right?
Okay. Yep.
Okay. Actually, maybe that other version is recursive too, but you could convert it to a loop. It's not a big deal. Okay. Now, just to give some context about what this tree is, right? What it just represents is operations that you do in what order. right? So the plus, represents, I'm going to add two things. And what's on the left is the left thing that I add, and what's on the right is the right thing that I add, right? And if what's on the right is more complex than just a leaf, then it sort of means you don't know the answer yet. You have to go do that stuff, and then you can do the plus, right? So in this case, it's like A plus what? I don't know. It's whatever this is. Okay, well, that's B plus what? I don't know. That's C plus D. Oh, I know what C plus D are. So I can add this, right? And then that gives me what to add to B, and that gives me what to add to A. So what the tree is effectively doing, I probably say this later too, but what this tree is effectively doing is it's parenthesizing your expression like this, okay?
Right.
And the way to remember that that's really easy is if you see parentheses in the equation, it's the same as like circling a subtree. Like if you can circle a subtree without cutting sideways, then that's the parentheses in the equation. Yeah. It's the same thing. Okay. Now here's the whole point of what we're talking about, which is you want to be able to not have to type this all the time, right? And it's natural, and everybody's used to being able to say something like A plus B times C plus D, but B times C is supposed to happen first. That's just something we decided as human beings that we want to do. And of course, plus and times are not the only example of this. It comes up in a number of cases, but this is the simplest one probably that people understand. That said, this one seems more arbitrary because like it is a human choice, but there's other ones. I don't know. I guess if you were willing to put parentheses around literally everything, this wouldn't be a problem. But it just comes up a lot, right? So if we run the same code on A plus B times C plus D, right? Well, this code didn't care about any detail of the operator, right? So we're going to get the same output, which is this same tree, except instead of this plus up here, we're going to get a times. And by this parentheses making that I just did, that gives us this. Right? I left out sort of the outer parentheses, but yeah, which is not what we would consider the right answer, right? This is what we would consider the right answer is parentheses in the middle. Okay, and then here's where I was gonna rant about the Dragon Book and stuff, but we already started that. So I will say, I mean, I went to college starting in 1989 when like all the web stuff hadn't happened yet, but a lot of this other stuff was considered old and established. And just the more I look at it, the more I feel like a lot of computer science was just corrupt, lazy people who didn't really solve problems. I mean, I hate to say it. And this is just one instance of it. And so these people weren't corrupt, lazy people. And even maybe the Dragon Book people are not corrupt, lazy people. They wrote a big book it's a really complicated book full of stuff, right? But there was this horrible malfunction that Casey already referred to where this book got used as the standard for how to teach compilers in basically every, certainly good school computer science class and probably everything else, because what else would you use? And the problem is it makes out parsing like it's really, really, really hard and like an entire science of its own, and doesn't say much about the rest of compilation, which is actually the hard part.
Oh, it's horrible for that. Like like if you read that book, you would assume that most of writing a compiler is trying to get a parser working.
Yeah.
And then you like generate some very simple code from the parse tree afterwards.
Now, just so people don't know, right? Just so people don't say you don't know what you're talking about. Like, oh, you went to school in the Stone Age. It's different now. So I have a current copy. Like this is what you would buy off Amazon now.
Oh wow! Can I see that? Can you hold up that cover?
Oh yeah, it's awesome. It's got a computer generated cover. The old Green Dragon book has a horrible, hand illustrated cover. Yeah. That's just not involving computers in any way, and so they replaced it with like whatever you could do in 1997 on a Silicon Graphics.
Wow.
No, before that, I don't know. Anyway, it has some additional chapters in the end where they talk a little bit about data flow analysis and like bytecode and stuff, but it's a small part of the book. And the problem with all that stuff is just they like touch on the topics, and each of these topics like really could have a whole book. And of course, I don't know. But the point being, like, I think the laziness is institutional. It's not, I don't wish to pick on the Dragon book too hard, because the fact is, the institution of computer science education could have, well, they did accept the Dragon book as the thing that they're going to teach, and that's what it is. They could have not done that, right? And gone out and dug up like a reading list of these old papers at least, or somebody else could have made like a different book. And
well, or you could say, this was the main thing that I was going to add about the Dragon book as well, is the Dragon book also, when you are handed it, at least I'm thinking of more I think it was a Red Dragon book that was the one that I saw, second edition.
Yeah, this is the more modern computer Dragon book.
I haven't seen that one. Yeah. But when someone hands you the Red Dragon book, they were like, this is the book to read about compilers, implying that somehow it's a good book to read about compilers.
No, people think that.
Is my makeup. If someone handed it to me and went, this book actually sucks, but I don't have anything else to hand you, that's fine. I've had to do that to people before, where it's like, I don't know of a good reference. You can try this, but it's lousy. The Dragon book's problem was people claimed it was good.
Yes.
Mainly.
Yes.
And it's not.
Yeah. Anyway, so if you look on the internet today, there's, as you know, a lot of trash information, and that's the main problem. There are some references that are okay. Like I said, I think a few minutes ago, when I went back and read this old paper, which is sort of what we're going to talk about, what it's based on, I think, although I don't know, because honestly, my eyes glazed over and I didn't finish the paper, right? But
John.
This is it's unreadable, dude. But so here's some modern references that are more readable. So although, okay, they do a couple different things, and we'll get into it. So this one is what I looked at last week. I didn't even really read this one all the way. I just sort of skimmed it. It's called Parsing Expressions by Precedence Climbing. Here's the URL. You know what? I'll paste this into chat for anyone who wants. If I paste this whole thing into chat, will that work?
Ooh,
people can pick.
You're asking a lot of Twitch there.
I am. Let's see.
Yeah.
No, it didn't. It didn't paste the whole thing. So here's part 1, and then because it's more than like a Twitter number of characters, and that was their competition or whatever.
While you're doing stream stuff, do you want to move your camera up a bit? You're off the bottom fairly frequently, I think, when typing.
Well, no,
okay.
I just don't want to. I don't care.
Fair enough.
Okay, so this one is the one that I read in order to figure out, but I sort of skimmed it. It's like, here's some code in Python, and the Python code, instead of like an enum in C to decide what you're doing, it like uses strings and like switches off the string. It's like, okay, we're not really reading this, right?
Right.
But it is the basic idea. Now, a lot of people like this book, Crafting Interpreters, which is also on the internet. And when I posted about this talk, people were like, oh, I know it's easy because I just read Crafting Interpreters, and it does recursive descent parsing, right? Okay, here's the thing. What they do in this book is recursive descent that will handle precedence. However, it's pretty slow and really ugly, and I do not recommend doing it that way. We can talk at the end about what this is, because it's kind of interesting in this, like, in terms of like how possibly stupid can you make it? This is maybe even one step more stupid than what I'm going to do. I don't recommend doing it this way, but it is like the polar opposite of the Dragon book. But I'm not bagging on the author of this book either, because he wrote a blog posting like 10 years before this book came out where he talks about the precedence thing that we're going to do. I don't know why he didn't do that in the book, though. Like, maybe he thought it was not as simple. I don't know. But the thing he does in the book is like, it's a little bit unconscionable. I don't know. Maybe that's too strong of a word.
Unconscionable?
Not quite. It's just, in that way when you write software, not you, when people out there in the world just write software and it's doing a lot of work for something that should be simple, right?
Yeah.
Yeah. And we'll talk about what that problem is.
Yeah.
The most approachable explanation of this is actually this paper called Writing an Interpreter in Go, which if you're writing a compiler, not an interpreter, and you don't program in Go, you probably wouldn't read that. I guess I forgot to paste the link in here, but you can find this by searching.
Mm-hmm.
Anyway, this is the most approachable explanation that I found. Okay, actually, and just to quantify what I did Saturday, right? So it took probably about 6 or 7 hours to do this conversion.
I would pause you for 1 second here in my role as interlocutor.
Yes, no, please interrupt as much as you want.
And just say, I think it might help now at this point to explain what you were doing. Because I think most people don't probably know exactly what you were doing, and they couldn't go watch maybe the previous video, but it wasn't all about that. It was about other stuff as well. So just like when you say tree rewrite, do you want to just give a quick example
go through a
so
quick,
people know what you did?
Quickie example. So what we were saying before is if you put A plus B times C plus D into this code that we showed already, you get this thing, which is the wrong answer, right? And like we said, it sort of gets built from the bottom up because it's the result of a recursive function, right? So what the code would do, after you've built C plus D, that part's fine. And we actually call this checking function that I'm going to mention in a minute about should we change the tree. And it looks at plus CD, and it's like, no, that's fine. There's nothing, that's vanilla plus, right? So then we get back, and before, let me just copy pasta this. What just happened? Okay.
Emacs power.
Yeah, exactly. So then you fall back one level in recursion and you had a times B and you were just waiting for this and now you got this, right? And you're like, okay, B times C plus D. Let's pass it to the tree rewrite code. And the tree rewrite code would say, hey, wait, I'm at a node that's a times and the thing on the right is a binary. And there's no parentheses, because when you parenthesize something, I would put a flag on the node, right? Okay. And it would say there's no parentheses. So I'm going to do a rewrite operation where I grab, you sort of like swizzle the tree around, right? Like, you basically want to turn this into, we can just, again, right? The right answer is, so this is, I'm going to put the outer parentheses. This is B times C plus D, right? Mm-hmm. Yes. And you want to turn that into B times C plus D, right? Mm-hmm. And so this is a right-leaning tree, but again, what I said about the parentheses is you have to be able to circle it, right? So this is like a left-leaning tree, actually. And actually that fact will come up later. So what it does is it rewrites into the following thing. Sorry, I should have deleted that first. It probably looked confusing for a minute, right? And how do you do this? You can do this just by, you keep the binary node with the left here. I mean, because it was the right that we detected, you keep the node with the left here, and then you steal the thing on the left of here, and then you move this one up and you child it. And it's a very,
Yep.
I don't want to try to draw those intermediate operations in Emacs, right? But you just, basically you don't have to make anything new because you have all the right pointers in the right places. You just have to change who's pointing to what, right?
Yep.
And that's what I did. And so to quantify this, the parser, without ignoring the tree change operation for a minute, the parser was around 6,000 lines last week, 6,300 or something, which some people would say, oh my God, that's really big. But like, it's a C++ competitor programming language with like a lot of nodes. There's like a lot of syntax. And so that's just what that means. The lexical analyzer was around 2,000 lines. The tree rewriting code was 350 lines. So it's like not even really that much code. But there's two things about doing things this way, right?
I'm going to interrupt you one more time, and I apologize.
Yes.
Just to finish up that part, you said you put a flag on things when there's parentheses. Yeah. So I assume that means something like, well, when you parse open paren, you then call like parse expression recursively or something. And when it finds the close paren, then you take whatever you got back from that and set the parenthetical flag, which then prevents any of these things from
Yeah,
happening.
yeah. It's
to
actually
it.
a
Is
little
that correct?
simpler than that.
Okay.
It's basically what you said with one small change that might be important for people to
Yeah,
understand.
yeah, please.
Um, yeah, when you see an open paren, you call parse expression, right? Um, but parse expression doesn't do the close paren. You do, because it'll stop whenever it sees something that doesn't start an expression anymore, right? Which a
Okay.
close paren does. So parse expression doesn't know what the close paren means, but you know
Got
that
it.
you expect that after parsing a full
I see.
expression. And if you don't, you can
You
say a
complain.
syntax error. And it's actually, so one of the things about these so-called recursive descent parsers that's a really strong suit is they're much, much better for error reporting than
Hmm.
all these other systems of generating parsers. And here's the thing: is error reporting is the user interface of your programming language. Like, it's critically important, right?
Hmm.
Um, yeah. So you don't want to phone it in. You want to be good about error messages. Anyway, so that's what I was doing, is I was rewriting this to this. Now, of course, because this is the right answer, the goal is like, how do you create this as
Hmm.
opposed to
Hmm.
having to rewrite it, is a way to,
Yes.
to say what we're going
Now
to do.
you said you wanted to say two things when I interrupted you, and I apologize. Uh,
Oh, well, so there were, like I said, I just like, excuse me, for some reason, the the Dragon Book Illuminati are trying to prevent me from speaking.
oh
Yeah.
yes, with the
Yes.
voodoo doll.
Um. So the reason I did this was I just liked the idea of cleaning up the parser, right? And finally understanding this thing that I had kind of swept under the rug and ignored. Um, there's something good about this tree rewriting aspect, which is it often makes code easier to write because you can just write code that parses some complicated construct. And, you know, if it, I want to call that from here, oh, but in some case when there's an operator to the left, maybe that operator has to know about this thing and whatever. And it's like, nah, just we'll fix it in post, right? It's like, fine.
Yeah, yeah.
Yeah. And so an example of, I mean, this is a very simple example, but there's in programming languages, there are a lot of like, binary operators are very simple. There are a lot of more complex constructs. So like in C, if you see the keyword for, which comes in one token, right? It's very unambiguous what has to happen after that. In C++, it's a little more ambiguous because they have ways of overloading it. But in C, it's like, actually, I don't even know. Latest C probably has some weird stuff. But in classic C, you see the word for, and it's like, okay, there's going to be an open parenthesis. There's going to be 3 statements with semicolons in between, and there's going to be a closed parenthesis, and then a block, which might be a statement, or it might, you just call your parse block function, which knows to look for either a statement or some braces and stuff, right? And you can write that in one function, and it's very clear, like this, and then this, and then this, and that, and that, and that. And, you know, sometimes when grammars get complicated, it's like, oh, well, I want to parse this thing in the middle of my complicated construct, but maybe it needs to associate differently or whatever. Yeah. I don't want to go too much into that because if you ever decide to do a parser that way, you will discover this. So there's a convenient thing about it is it lets you paste over things. Another way to say that is like when you decide to parse things in the middle of like just a hard-coded function like that, like the way the specific subfunctions that you call determine precedence in a way, right? And if you don't want to have some system for negotiating precedence, you could just fix it later. And it makes it easy. But it's one of those things where it makes it easy in the beginning, but then like later after you've done it a bunch, there's like a lot of code, and it's not a ton of code. Like I said, it was 350 lines, but it's like, oh man, I really have to like, if I have a bug, I'm like not sure if it's over here, over there, and like it was more complex than I would like, right?
Right, because
Especially,
you can't step through the recursive descent parser anymore and know if it's operating correctly, because it could be that it's operating incorrectly, or it could be that it's operating correctly and the tree rewriter is operating incorrectly. So now you have to debug both at the same time
yeah.
effectively, which just makes your job a little bit harder. Not
It's
fantastically
yeah, a
so, but
little
a little
bit.
bit harder.
It's actually not that bad because they are interleaved. Like the tree rewriting doesn't
Right.
operate at the root of the tree. It's like every time we're going to pass you something back, we call the thing, right? But
Right. If it was fully deferred, then it would be a real nightmare.
I would more classify it as just like it's harder to think about. And that's one of the reasons why I want to talk about this today. Again, The goal of this is expressing how absolutely simple this solution is. And we're in this world where we're like complexity bound, right? Like software is limited by how hard things are to understand. And that's why I think this is such a critical issue. Like anytime you can identify something like this, like we need to nuke all the overcomplicated stuff from orbit. It is the only way to be sure that like software will be good in the future. So yeah. Anyway, okay, here's where we bust out the spicy meme, right?
Oh.
So I made a spicy meme just for this talk.
What?
So what I said was, this thing that we made is wrong. Okay. Because, not in this case, not in the plus case. Actually, here's another thing we'll say for later is like, if you're just plussing a bunch of integers, you actually kind of don't care about precedence here, right? If you're doing pedantic floating point, maybe you care. I don't know. But, so there's some things where you don't totally care, and we'll come up to that later again. Anyway, the point was, if you do A plus B times C plus D, you get this structure, and it's wrong, okay? But here's the spicy meme.
I'm so ready for this.
Yes. The spicy meme is that it's actually right sometimes, right? There are some cases for which...
is that... I mean, is that going to Twitter, I hope?
Sure. Yeah, nobody will know what it's about, but...
I mean, that has to go up right now.
So it's actually right sometimes. And this is the key insight to these papers and stuff, which is here. Let's say you have an expression such as A is greater than, like there's an if statement around this, right? You're going to say, just to provide, if this, do something, right? That's a real thing that happens. If it happens to be arranged in this way, the precedence of greater than. Now, if you're just thinking about math operators, it might be weird to think about greater than is like the same thing as plus, but in terms of a programming language, it basically is. It's an operator that takes two sides, it returns a value, that's a Boolean, right? And so, but the precedence in C-like languages, for example, of greater than is very low. It's lower than plus, and plus is lower than times, okay? And if you parenthesize this, you get this, right? And the tree version of this, of course, is this, which is exactly what that code outputted, right?
Right.
So like, this is right sometimes. And so maybe you can use that, right? That's, well, the dumb guy on the bell curve is like, well, I guess that's what we can do, right? And then the smart guy is like, no, like this means something. It's like the mashed potatoes, right?
Yes, the mashed potatoes.
This means something.
Yes.
Okay. Well, okay, if this is the right thing for this, what if the precedence goes the opposite way? Obviously, you could write this thing, right? And it's parenthesized that way. And that's a left-leaning tree. We just spoke a little bit ago that you could turn the right-leaning tree into a left-leaning tree by rewrites. But if you wanted to just generate it, how would you do that? And the answer is basically what Casey was asking about before. I'm trying to remember what I did here. Okay, so here we have a version of parsing a binary tree where you pass in the left side as a parameter, and then you just keep calling this to get the times B plus C less than D, whatever, right? So you pass in the left, you say get the next token. If it's a binary operator, make a binary node. Otherwise, just return the left side. And this doesn't have to be a function. This could be inside a loop, but for clarity, I just broke it into a piece, right?
And just to be clear, if I can just restate that again,
Yeah.
Make sure everyone gets it. So basically what John is saying here is when we write the recursive descent parser the first time, it was an arbitrary choice for us to decide to build a right-leaning tree, meaning we always were putting the next token underneath our own binary operator. But we are not forced to do that. We could have just done it the other way, where we always put the thing on the left side of the tree, and to do that we have to pass down that to the recursive call.
Yeah, and so I think it's sort of which way you find easier to think about depends on just how you tend to think about and solve problems. If you went to recursive school like I did, you probably build the right leaning tree by default. But iterative algorithms tend to be more efficient than recursive algorithms, right? I don't care what all the tail recursion stands say.
Yes.
So, if you're trying to build performance software, you want to think about loops and that kind of thing, right? Because, loops can be expanded into like loops operating on a wide number of things and whatever. Okay, so if you have this thing that takes a left-hand side, then you can just, every time you make a new subtree, you can just pass that in as the left-hand side and build more tree, right? Which is what this thing is doing. This thing, another way, instead of parse single binary, you could call this like add the right-hand side onto a tree or whatever.
Right.
Right. And so this version of parse expression starts by parsing a leaf. And this is the thing that's weird for me to think about, because in the recursive version, the recursive function itself is like, I'm going to parse a left and then a plus, and then the right comes later. And in this version, you give the left and the left comes already. And that was weird for me to think about, but the recursive version is hard to think about too, because you have to be like, oh, this comes way later after things happen. So I don't know, right? But anyway, so here's how this works is you get the first leaf, which in this case is A. Then you do this loop where you parse binary, that'll eat A plus B, right? And then if it returns the same thing we gave it, this might be a stupid way to do the stopping condition, but it's just the way I did it, right? Because if this doesn't see an operator, it just returns back the parameter.
Right.
So like if we just got that, then just return, that's the answer. We ran out of input or whatever, right? Otherwise, just say the left is the new binary node and then just keep looping, right? And I believe that's what you were suggesting before.
Yes, I was kind of asking like, or I wasn't even suggesting you would even necessarily use recursion. I was just saying like, I just grab a token, I put it down, I grab another one, I go, okay, it's a plus, I link it to the left side, I grab the next one, it's,
Yeah, that's exactly what this is. Like if you
Yes.
don't make this a separate function, right?
Yep.
If you just like put it, I'm not even going to indent, but
Yeah.
Yep. Yeah.
Exactly. So that's exactly what I was asking. And so I guess you're saying, well, we could totally do that.
You could. And that just gives you this tree this way, right?
Yep.
Which is A first, and then A plus B comes next. And then we just keep attaching, little fronds that reach up as we keep going, right? And of course, again, this is right sometimes. This is right when precedence is going down, okay? And the key insight is that that's all you need to solve any problem, is what's right when precedence is going up, what's right when precedence is going down. Now, I don't think these papers ever express this way, but that's maybe my contribution, is just to like think about it in a slightly wacky way like this, all right?
Yep.
Okay, so these two things are all you need, right? So if you do the recursive thing, that's right when precedence is increasing. The loop is right when precedence is decreasing. But you don't really, it's not that hard to put them together. You might think about like some high level thing that shifts back and forth, but no, it's actually very fluid. So here is code that combines both of these things. This is a recursive thing. And again, I keep saying recursive, but you could turn it into a loop. Recursion just is a way of using the programming language's stack as a stack data structure, right? And so if you want to make your own loop version of that, you just make a stack of your own. But I just, for simplicity and brevity, I made it recursive, right? So here, as long as we keep seeing operators of increasing precedence, we do the right-leaning tree. And what that is just, as a parameter, now we're passing in the left-hand side, which we did in the previous version, and that's part of putting these together, right? And then we pass down the precedence, which is just, how do you know it's increasing? Well, every time you get an operator, you look at the precedence, right? And the first call to this passes like negative infinity or whatever your range of precedence is. Every time you get an operator, you say, what's the next precedence? If it's lower or equal to what we have, then just pretend like we ran out of input, basically. Just return that thing, right? Otherwise, just do the thing we did in the recursive version before, where we make the right-leaning tree by parsing another expression and keep going, right? So as long as precedence goes up, we make a right-leaning subtree, right? Now, back here, we have an outer loop like the version that we just saw. And instead of, in this version back here, we were parsing one binary node, and that gave us this. Instead of just parsing one binary node, we just say parse as many as you want as long as it keeps going up, right? And then come back around, and that's our new left-hand side. And then just pass that in again. And that's it. This is the entire code that handles operator precedence, right? And so you alluded to like seeing small amounts of code before.
Yeah, that's what they look like, yeah.
This is like the first half of the Dragon Book.
Yeah.
Like, that's an exaggeration, but not really, because like, this is the only real problem that you have when making a programming language, is to decide, well, no, when parsing a programming language, no, there's plenty of problems later, but when parsing stuff, you just need to decide, you know, what is the input text actually mean? There have to be rules that determine what it means, and those rules need to be clear, right? And there needs to be an implementation of them, and this does that. And so we did do a little bit of a leap between this one and this one, because it's like, we keep passing this left tree through the loop, and like, what does that mean, right? And by the way, this might at this point be substantially different from what's in those references, because again, I didn't really read them. I just figured it out. But I kind of feel like it has to be the same thing, because
it's roughly the
what
same.
Else are you going to do?
What I remember.
Yeah.
There's a bunch of different ways you can phrase this operation, but that's what it is. Yeah.
Yeah. Okay. So now let's show an equation that is not monotonically increasing or decreasing, right? And like, how does this work? So here's one where we sort of started doing our A greater than B, right? This is the increasing, but it's got a plus E on the end, right? And so the right answer for this is this. You want to make sure to do the times first, which in this case, if we do the full parentheses version, it looks like that. And so if you convert this to the tree, just by that rule of like, can I circle the subtree? This is the right answer. And that maybe looks like a scary tree, but it's actually not scary, because it's two right-leaning trees glued together, where this X here is just this tree, right? And we already know how to make these. These are made by the stupid parse increasing precedence code, right? So that's basically how this works is, well, I stepped through it. Let's see if I still remember how to explain. I basically went through it literally every step, and maybe I should have actually put it in a program and stepped through in the debugger, but I didn't. So let's go split screen, and we can keep the code up here.
Okay.
Right, and then over here. So this part, when I say parse and then a number here, that's just a call to this parse expression, I think. Hold on, or is it a call to the?
Probably yeah.
I named them both starting with the word parse. Anyway, so we start out, we parse a leaf, right? Oh yeah, so we parse the leaf, that's going to be A. We pass it into parse increasing precedence, okay? That's going to see the greater than, so I must mean this.
Yeah, that's what I was like, it has to, because the other one doesn't build a tree.
Oh, because yeah, this is recursive, right? So so this call to parse one just means calling this function again recursively. It could be an iteration of a loop again. Don't fixate on the recursion part. Parse one again makes a tree. Like we were saying before, we keep making subtrees and waiting till later, right? So we do the greater than, we do the plus, we do the times. Till now it keeps going up, so we're fine, right? When we do D, hold on, let me paste the original equation. So we call parse 3. Parse 3 sees D, and then it sees a plus, right? But the precedence that we passed in was the precedence of times, which is higher. So you can't go down. So we just return D instead of saying D plus anything, right? So the recursive version stops here and gives you this tree, okay? And then this is just showing how that tree gets built, because we're recursing back up, right? So we got the D back. We had C times something. We had C times parse 3, right? The result of parse 3 is D. So we have C times D, right? And then parse 1 was B plus the result of parse 2. B plus the result of parse 2, right? And so on. So we build this tree. Now, this subtree gets returned from here. And then the node that we got back is not equal to the left-hand side that we passed in. So we continue. That's our new left-hand side here, this B plus, wait.
That's right. And then you pass it to, like, you parse the plus and call parse 4. There should be a parse 4 above, like, in between these two, sort of. But
I think, okay, hold on. I left out a step somewhere. I left out a step.
No, you didn't, because that's the left. You got back the left, and then you're going to call parse increase in precedence, passing that tree, which is going to parse.
Oh,
the
yeah,
plus,
yeah. Okay.
Parse 4.
Yes.
Like,
yes. So
you just left out a label.
I left out. Yeah. The secret of why this works is, and this is an important change from the earlier version. You know, in the early versions of the parse binary tree, it would like call itself. This is why I remember really early on, I'm like, I don't remember why I put this one in. It's because of this. Because I wanted to introduce a version where the old parse binary calls back to parse expression instead of calling itself. Because what actually makes this work is every time you get back a new subtree, this loop keeps trying from the precedence that you used to start parsing that subtree, right?
Right.
And that's how you get this right here. This funny shape is you got back this subtree. This greater than is still waiting higher up. It's like we parsed that input, but it's like on the stack, right? We haven't returned back to it yet. So we see this. And then what we came in here with, this minprec, when we've got this, is the precedence of the greater than, right? Because that's what our caller said. You know, you have to stop at any greater than or anything greater than the greater than. That's
anything
confusing,
greater than,
right? So so here, you know, plus again is higher precedence than greater than, so it's fine. So we do our binary tree then, but you know, instead of having a leaf as the left-hand side, we have this whole thing that we passed in, and that calls parse 4, which gets the E. There wasn't much left. It was just the E. So then this returns that back, and then this loop loops around, and there's nothing new. So we return this whole thing here, and then the caller attaches that to the greater than, right? And so we get this complex tree shape. It's pretty simple. Like it's a little bit complicated to think about in the way that any tree operation is, I think, in that like, oh, just step through it and see. And I don't expect this explanation. I expect a lot of people would still be scratching their heads a little bit. But if you just go through a few cases, it's like pretty obvious what's going on, right? And this is basically the whole problem, right? Now, well, why is it the whole problem? What about other stuff besides binary operators, right? So like in C, you have like array subscripts. This is actually easier than a binary operator. It actually is an array subscript is a binary operator because it's the thing you want to subscript and then the index value. It's just got a little bit more syntax, and that actually makes it easier because you don't have to worry about what's on the right-hand side of this bracket. It's like, okay, we just stop the index here. So the way that this works in our code is we just treat the left bracket as a binary operator in the precedence table, just like anything else, right? We actually use the ASCII values for most of these. There's a few, you know, when you have multi-character operators, there's no obvious ASCII value, so those don't. But, you know, we just literally have the ASCII value for this. And that handles array subscripts. You know, here's an example of another kind of thing that the tree rewriter used to do that's handled naturally by this system is like, if you say s.a sub b, right, and you have some special function that does, even though array subscript is pretty simple, you might have some like we have some weird modifiers you might have, but we basically do a function that's like the for loop thing that I was talking about, where it's like, oh, if you see a bracket, just expect, you know, parse that, parse an expression and then expect a close bracket. It's very simple, but it's like a few lines of code that are right there. And if you do that, you end up with I don't have the wrong one, but you end up with S dot A sub B is sort of the tree that you end up with again. That's why precedence matters here. This is meaningless. If you don't know, like what, this is like a struct and we're dotting and there's an array element of the struct and you can't evaluate this without knowing the struct. So it's a terrible way to have the tree, right? You actually want this, you want S dot A subscript B, right? And that's why you need to fix the precedence for this kind of case. You can do that either through tree rewriting or through the thing that I did here, or I mean, I guess we have to talk about the crafting interpreters one at the end. Okay, so yeah, I mean, this is just to show that it matters what's the thing on the left, just like any math operator, right? Like a struct subscript operator has precedence just like a math operator because you want this text to turn into that. But if you just change this character to a plus, you want it to be different, right? No surprise to anyone who's experienced, but just an illustration. Yeah, I mean, this is just, in order to handle the close bracket, this parse increasing precedence loop, basically, it's like, look, do the same thing, make sure it's a higher precedence than what we had. And then like one way you could do it, which is what I actually did, is like, look, if that operator was the left bracket, just call this function that also handles the right bracket, right? Again, it's a small thing. It could be inline here, but you know, otherwise just maybe it's a binary operator, so do this, right? And
do you do that for parentheses as well then, or?
Yeah.
Okay.
Parentheses are very simple. Parentheses just says call this parse expression.
Right.
With again negative infinity for the precedence because.
Right, because you're restarting.
You're restarting. Yeah, it's like it's in a black hole in its own universe, right?
Yeah.
And then you do that, and then you come out, right? And then function calls are the same. You know, they're syntactically they have a little bit more to them. But we talked about the for loop. It's the same thing for a function call. It's like, oh, I see, I saw an expression, right? Because it could be an identifier, but it could be like dereferencing an array of function pointers or whatever, right? I saw an expression and then an open paren. So we're going to start parsing a function and then, you know, look for commas and look for expressions and then look for the close. So that's, logically speaking, it's all handled the same way. Like anytime you want to do a more let's say more rigid syntax than something like binary operators or something, or a more elaborated syntax, I don't know. But these all, like the thing about these programming languages that I don't know if it's luck or necessity or what, but anytime we have these more elaborate syntaxes, there just isn't really ambiguity that's not handled by this. Like, again, you do the function call and once you're in here, you're in parentheses and like you can't bleed into the outside world. So what are you going to do?
And right? Wouldn't the commas just be automatically handled by operator precedence anyway?
Depends on if comma is an operator. In C it is, right? And so yes.
Even if it wasn't, you could parse it as if it was using this parser, could you not?
Yeah, I mean, okay. So there are a few different ways you could do stuff like this. I'm trying to remember if we do this for commas. I think we do. Like, so in my language, comma is not an operator, which leads me to be motivated to handle it differently. But in C, you have two choices about how you want to parse this. One is you could, if comma was very, very low precedence, which I believe it is, like if it was at the very bottom of the precedence table,
yeah,
you could like pass that in as the min prec that we were showing, and then you'll stop at comma, and then you parse the comma, right?
Yeah.
Another thing you could do, which is something that I do for other things, I don't remember if I do this for comma, but in addition to these two parameters, I do have a third parameter, which is also in here, which is just like some control flags about what you're allowed to parse right now. And it's just like, look, are you allowed to see an open brace here as the start of an expression or not, right? So like in C, you have open brace could be part of a literal, or it could be code. And I don't know. You have a choice about how to handle that, right? But that, I think by the time you have those three parameters, the left tree, the min precedence, and the control flags, like you basically can do anything. Like there's no, and it's much more expressive and powerful than having to fit it into some weird like stack machine like from the Dragon book. So, oh, what was I going to say over here? Oh, your other option of how to do this is to actually just parse this as one expression. And then again, just say, oh, is it a binary operator that happens to be comma? Okay, that's the first argument. You have a little loop that like untrees it that way, right? That's the great thing about programming is there's multiple ways to solve problems. Okay, so I sort of skipped over this thing about equal precedence. I talked about plus not really mattering. The official rule for this that you will see in those papers is that it depends if it's left or right associative, right? So if your operator is left associative, which most operators are, there's really almost none that are right associative. Someone in a paper had, or one of the blogs, had the example of an exponent operator, which I guess that makes sense that that's right associative, right?
Yep. Yep.
I don't have that in my language. C doesn't have it, so whatever. But if you had that, then there's a few ways of how to handle it. You could have an if statement. You could have an extra, because my precedences are integer, and I hope most people's are, you could bias, like when you do this comparison, where is it? This one, right? You could add, is it -1 or +1? I don't want to think about it. But the point being, you could have a number that for most operators is 0, but for right associative is 1, and that allows you to continue in the loop. Right, it would have to be -1, I guess, or +1 on this side, right? And that would just say, stay in this loop as long as it's the same precedence, which is what you want to do for right associative operators. For left associative operators, you want to do the left leaning tree thing that your loop would have produced, right? And again, in my parser, I don't think about this rule at all because we have no right associative operator. So
right,
it's not even a thing. Yeah.
Because it will always left associate by default because of the way you're passing the argument down and making that decision.
Yes.
You don't need to do anything. Yeah.
Yes. And then that's literally everything. Like, and it's so disappointing. Like, on the one hand, this information is out there in various forms. You could follow the links that I had earlier, but like, there's just so much confusion around it, and so many, like people pretend like it's science or whatever. But like, all this really is, all we are doing here is saying it's almost tautological. It's like, look, the tree is the parentheses. So we just need the tree to be the right shape, to be the parentheses. And how do you do that? Okay, we need to compare precedences. Like, and I guess it's a little bit clever that it's not that much code, but it's just, it's staggering to me how people make a big deal out of it. Like, I don't even know. I mean, I guess, if you're newer at programming, I'm sure this seems very complicated, maybe, right? But like, if you've ever shipped a commercial video game, like this is so simple compared to so many of the things we do. Yeah. The only thing that I could think about is to talk about the crafting interpreters one, unless you had other topics or questions.
Yeah. So I guess I'd like to just ask sort of one follow-up question, which, I could probably guess what the answer is, but
yeah,
it would be, why do you need anything other than this? So it sounds like, from what you said, that effectively the reason why you need something other than just a loop that does exactly what you just described to parse everything is because of programming constructs where the symbols mean something different because a previous symbol told you they would. So for example,
Yeah.
you said for loop.
Yeah.
I'm just trying to be concrete here.
Yes. Yes.
So you see a for statement, and suddenly the meaning of semicolon kind of changes. Like normally in C or C++ or most languages, you couldn't have a open parentheses, some stuff, and then a semicolon,
Right.
because the semicolon is a way of ending a line.
Yeah.
And you're ending a line in the middle of a for statement, which, in general, in the middle of a parenthetical,
Yeah.
which you wouldn't normally be able to do. But because it's a for statement, that's not what that means. So I'm assuming that, let me make a sort of bold statement here, being someone who doesn't write parsers. So I'm just going off of what you said.
Yeah.
Would it be possible, do you think, to write your entire compiler using just that loop, and the only thing you would do is have different precedence tables based on that you could switch when you saw keywords? Like is it really is really all of parsing just we do some left and some right in alternating? Because it seems like maybe it would have to be, since those are the only trees you could produce. Or are there actually things where it's like, no, you need to actually custom parse some things, not just because it's easier to write it that way and to report errors, which mean, or is it basically programming languages? No, they just don't have things that couldn't be parsed this way in general.
So in this case, you would make semicolon a really low precedence operator. You still have the weirdness where you have a few weirdnesses with semicolon specifically, right? So in the for loop case you're talking about, it acts like an operator because there isn't one on the right, although I believe you could optionally put one, right? But typically you're allowed not to, right? Which is weird, right? But with statements, you're not allowed to not put one on the last statement. But you are allowed to put 5 in a row with nothing in between. And so like your normal operator parsing would have to add complexity to deal with that anyway. And so when you're talking about things this simple, it's a substantial amount of complexity. So relative to the base. And so I don't know that I would ever seriously try to do it that way.
Right.
But
right.
it might be a fun thing to do. The thing, so just for context for people, we've sort of been focusing on this, like parse expression is like an expression in a programming language is just like one of the fundamental units that could be in most places, right? I don't know if there's a better explanation than that. Probably there is. Probably the Dragon Book has a 17-page explanation of what an expression is that nobody understands. But usually you have, at least in a C-like language, you'll have one higher level thing, which is like statement level, which would handle the semicolon, right? And there are things that are statements that are not expressions, like a declaration of a variable is a statement, but you can't have it down in the middle of stuff, right? And so you already tend to naturally make this hierarchy of functions that parse specific things. And I would say that is actually the attraction of this kind of parsing, which again, I'll say recursive descent because that's the name that people know, but like, it's not that complicated. Right. Like calling functions is a thing that we do. It's like not rocket science to call functions, and that's all we're talking about. So you have a function that parses a statement, and that's just very clear. Right? I mean, sometimes things get messy when you make them complicated, but at its core, everything is laid out right there and you see it, right? And that's very good. It's very underrated, actually. So the thing that you're talking about would obfuscate that to some degree, I think.
Oh, yeah. It wouldn't probably be good for error reporting, as we talked about, right?
Because or understanding the code, honestly.
It's going to be like operator precedence error. It's like the only error in the programming language.
Well,
you're like,
dude,
what?
Back when I was in college, like shipping GCC or whatever, still would tell you shift reduce error or whatever when you got a syntax error. Yeah, shift reduce conflict.
Yeah.
It's fucking awesome,
And you're like, dude, I don't care how you implemented the parser.
Yeah.
Like,
so bad. So bad. Okay. Let's talk about this. Let me see if I can find the crafting interpreters thing. I did say it's very slow and you shouldn't do it. This is true. I don't wish to bag on it too hard though, because it's also kind of awesome.
Okay.
It's kind of awesome.
Okay. Okay.
All right. So before we go look at this one, let's go back and remember sort of the property that makes this work for weird arbitrary tree shapes is that this loop here keeps trying from the earlier precedents, right? We keep parsing right-leaning trees and then gluing them on. But it's like this loop is like the thing that makes it work, right? Okay. So now I'm hoping, I actually had the paper copy of Crafting Interpreters. This is the online. I don't know if it's the same, but it was chapter 6 in my copy. So they talk about BNF grammars and stuff, which I wouldn't encourage you. Here's the explanation of the precedence problem. Again, I didn't really read this either. I skimmed it. Okay, recursive descent parsing. He's first parsing some stuff made all out of equal signs. So the precedent, that's like our plus sign example. Okay. Now, I had to read this like 5 times to understand what was going on because it's like.
Can this be made any bigger? It's kind of hard to read.
Yeah.
There you go. Perfect.
It's pretty stealth. How? Okay. So like the precedence explanation starts here, and like I read it and I was like, where's the where's the precedence, right? And okay, I just want to encourage people. There's a class of explanation that you read it and it seems like you get it, but if you think about it, you realize you really don't get it. And because I had just worked on this problem, I read this text and I was like, dude, I just implemented a parser that does correct precedence for our corpus of 700 tests and our shipping game that's 300,000 lines long. I should understand this, and I had to like step through it to understand. So I guess part of that though just speaks to the difficulty of explaining concepts in text sometimes, right? But okay, so somewhere up here, there's a couple of sentences. I don't even know if I'm going to find it. Yeah, it's all in Java, by the way. Have fun with that. I can't find it. Okay, we'll just look at the code. Like this is how stealth it is. So what happens is you implement a bunch of functions. Instead of one function for a binary operator like I had, you group your operators into precedence levels. C does this. There's like a table of what operator at what precedence. And so for each precedence level, you make a separate function. It's sort of like COM where you have to make a separate class for every button or whatever.
Right. Yeah.
Okay. But this is also what's awesome about it, right? Okay. So minus and plus in this toy language that they're parsing are the lowest. I guess the double equals is comparison. So it starts actually up here. So comparison says it's got a while loop. Remember I said the while loop is the workhorse that makes this work.
Right.
While the precedence is going to be equal or higher, you keep doing the thing, right? So here we say, this is just parsing, and what does he call comparison? I don't know. Anyway, this is the equivalent of our parse expression. You would enter here, and okay, maybe an expression is a comparison operator. If it is, well, we have something on the left.
Right.
That we parsed, just like the version that you were talking about. So we parse the thing on the left first, actually. Then we look for the comparison operator. If it's one of these, then parse a thing on the right and then make a binary tree, just like I was saying.
Okay.
The weird stealth magic is, okay, well, you'll note this isn't comparison, right? It's a thing called term.
Yeah.
What's term? Term is this thing down here that's like, oh, higher precedence operators, right? Maybe it's not one of these. Maybe it's a minus or a plus.
Right.
So do this, right? Okay, but what's on the left? Because we have to pass the left in. It's factor. What's factor? It's this thing down here. Factor is like maybe it's times or divide, right?
Yep.
And okay, but maybe it's a unary operator, right? Or maybe it's primary. And primary is what I was calling leaf of the tree.
Right.
I didn't like the word primary because... So he has simple stuff here plus this, but like all the for loop and whatever that we're talking about are essentially, they're sort of tree leaves relative to everything else, except they have complex structure inside, right? Again, they're like a black hole or whatever.
Yep.
So this actually works. And I had to convince myself that this works, again, by taking some of my test cases and like stepping through. But it literally does do the right thing. It's as if you took
Yeah.
any notion of precedent, you got rid of all the data in the solution that I talked about, and you
Yes.
baked it completely into code.
Yes.
Now, the reason I am saying please do not do this is the following. Imagine your input is the number 3 or whatever. It's time to parse a 3.
Yeah.
Which is common, or the name of a variable. Like, these are all over your program, okay? What do you have to do to find out that it's 3? You're like, maybe it's greater than, right? Maybe it's maybe, and then you come down here, right?
Yeah.
And so it's not very efficient, firstly, and then secondly, the thing is, it's not very fluid with respect to if you're working on a language and you're adding new things.
Yeah.
Where does this go? Oh, maybe this should be higher precedence than this thing. No, let me move it down here. This is kind of inflexible in that way, and maybe easy to make copy pasta errors or whatever, right? Because you have to keep making all these functions, and then who calls who has to change around anytime you change a precedence. But I give it the gold star for like the most hard-coded, baked-down implementation, right?
Yeah, you can type it in entirely in just a top-down style without needing a table or anything.
Yeah. Like, hey, my embedded CPU does this. It uses 0 bytes of memory. Anyway.
I think on an embedded CPU, you probably really wouldn't want this, but okay.
Well, yeah, I don't know. Somebody in chat was saying he talks more about precedence later, and maybe I missed that part. But like I said, I missed most of this part. Like, I had to read this like several times before I understood what it was doing, because it just looks like redundant recursive function declarations for binary operators, and it's like, okay, it is that, but the hierarchy of the functions does the work.
Put in terms of the way that you explained it, with the like, we need to be able to build left-leaning trees and right-leaning trees, and then we need to interleave them as necessary.
Yeah.
Essentially, what he has done here is just said, well, I am going to make the recursive call part build one side of one lean, and I'm going to make the while loop build the other lean. And because each step can do both, we now have the ability to make left-leaning and right-leaning interleave. Done.
Yeah,
we have solved the problem, right?
Another way to say this for people is, instead of passing like the minimum precedence as a parameter, it's like you made a bunch of copies of the function, and you put the name of another function is essentially the minimum precedence of what you're allowed to parse now, right?
Well stated. Yes. It's almost like you had
don't do that.
You had like template, like less than minprec close, and you just made an instance of every different operator precedence as a function. And called it.
Yeah. Don't do that. I don't recommend that. Again, Robert Nystrom may recommend it. He may not. I don't know why. Again, I know he knows the other thing because he wrote a blog post explaining it 10 years before this. So this is not to bag on the author of this in any way. It's just, I would not, if someone working for me wrote this, we would have a conversation. That's all I'm saying.
I see.
But maybe it's easier to understand. I don't know. People can tell me if they find this version easier than the minprec version. I don't know, but that's it. That was, so I just wanted to say, again, I don't think any of this information is super new, because there's people out there who know these facts. It's just, again, when I went to go read things, like when you go read a source of technical knowledge, these days you really have to be asking yourself how much you should trust it, right? That was less true before, although, as we know, we talked about some examples that stretches way back into time. And so, the problem when you go trying to read about this stuff is you don't know what to trust. And if I don't know that I should trust something, maybe there's a personality difference between us. If I don't know that I should trust something, like my energy investment in figuring out if I should trust it depends on how many other options I have, right? It's like, if this is my only option and I don't know how trustworthy it is, what else am I going to do? I'm going to figure it out. I'm going to study this description and try to understand how it works. If you have an entire internet full of other stuff, I'll just search for something else. And like, there's just so much noise is the problem. And it's really so simple. And so I just want to try to signal boost a little bit. I mean, that's the reason why I wanted to make it a public stream, is we could put it on YouTube next to the other thing. And it's a nice bookend to that question that we had about how to do precedence. And I was like, oh, just write some code. It's like, okay, well, no, you would actually call this an algorithm.
Yeah.
Whereas the thing that I used to do is not even really an algorithm. I mean, you would, the way that people use the word algorithm these days, everything is an algorithm. But the thing that I did before was like, look, just write some code to fix the thing.
But not the algorithm, which
yes.
Of course is something totally different.
Yes, of course. Anyway, I was also hyped that it was so simple and so easy to figure it out. So I was like, hey, let's just do a little talk and go through it.
I would also say that like it's good. I think your explanation is good as well for people who want to understand. So shunting yard is a good example of a literal algorithm. Like here is it's an algorithm with a name and everything.
Yes.
And you can understand it much better once you've walked through it the way you have, because as you pointed out, it's basically just doing the same thing, but it explains it in terms of just if you just have a stack instead of having an actual recursive call of some kind. And stuff like that. Yeah. So it's just helpful to understand as well, to have more explanations. More explanations are better because there are, like you said, a bunch of people who have done something like this, but it's not always easy to understand why their thing works or what it's doing. But it's always doing this.
Basically, I mean, the correct output is predetermined, right?
Yes.
And so therefore, I mean, there's some freedom in what the implementation could be. Obviously, we just looked at this other one, but like, it's kind of constrained by how complex could the mapping possibly be, right? Like at some point, if your implementation is so complex, you must be doing a lot of extra stuff that could be simplified away, because the input is not that complicated and the output is not that complicated. It's just like, yeah. And I don't understand why this has been made so hard. I mean, I'm frustrated because, like, look, dude, my hobby in college was making toy programming languages. And at first I would do, parser generator kind of stuff.
Like Yak.
Yeah. Like I made like 11 or 12 of these, right? And then I very quickly graduated to like, yeah, this actually sucks if you use it and you know what you can write on your own. So by the end of that process, was fully on the write your own lexical analyzer and parser train. However, I actually don't remember what I did for precedence back then. It's weird. I know I did something because the stuff worked. And it's very frustrating to program in a language that has an infixed notation and no precedence. But I don't remember, and I don't have any of that code, I don't think.
You've got lerp. What'd you do in there? Tree rewrite?
Lerp was weird because I didn't. Yeah, I could go look. But like I maybe wasn't concerned with this kind of thing yet anyway, because okay. I was more doing this weird like database as a primitive thing. And yeah, I don't know. I mean, it certainly had a lexer and a parser in it, and so I could go dig that up. But yeah, I don't have any of my college day code around, so I wonder what I did. But yeah, it's just like, how do I go this long and not understand something so simple? And maybe it's my fault. Maybe I'm dumb, but I don't think so. I think like, even like, you go on Hacker. So this thing, one name for this, I think, is a Pratt parser, which, I mean, I'm conflicted about names like that in general because, it's because of this original paper that like I don't understand. But give credit where credit is due, but also I feel like when you name stuff, you make it sound complicated. And then you go on Hacker News and there's people talking about how Pratt parser combinators are the future of computers or whatever, and you're just like, oh my god, guys.
Like they're like new advances in reverse Frobination or whatever, and you're like, what's that? And you're like, oh, we've almost got this new like theoretical parser to run at 1 character per second of input or whatever, and your head explodes about why they are still like looking at this stuff. But
yeah, exactly. We throw an exception per character.
And so I can understand the exacerbation, but to be fair, that happens in literally everything. Like there are people rat holing in theoretical stuff for everything. Which is fine. Sometimes they find something.
Someone says lol, but the book explains that in the next part. Let's just look, because again, my goal here is not to denigrate anything. But I mean, I read the thing and it sounded like I had gotten to the end of so recursive descent. This is all the stuff we looked at. And then it talks about syntax errors. And I was like, okay, parsing must be done. Do you mean?
Yeah, that seems like the end. Yeah.
Do you mean part 7? Wiring up the parser. The error handling. Delete the blah, blah, blah. Design note, logic versus history. Should we put where? Okay. Yeah. So he's talking about that, which I probably agree with. Okay. So this is like a side note about precedence. No, this is a side note about backward compatibility.
Yeah. This is not really about that.
So do they mean part 7 next?
Evaluating expressions.
No, because that's iterating over the tree and like.
Chat. What are you talking about? Be more specific, chat.
Oh, wait. There's someone has given me a specific link.
Yes. We needed chat to be more specific.
Where the link isn't opening. Chapter 17. Oh, so by the next part, you mean chapter 17. I mean, I think that's fine. Again, like maybe the advanced stuff is at the end if you consider that.
But that's not that. I would say no, because if that's what you were handed as your first explanation, though.
Yeah.
Right. It's important to explain it clearly the first time. That's kind of what we're talking about. Like, obviously, anyone who becomes an expert in parsers will know about Pratt parsers or whatever else you want to call this sort of stuff because you'll study the problem a ton. The point is, if you're someone who doesn't want to become an expert in parsers, you just want to write a parser, the first explanation should explain this. That's the whole point of this whole thing. The Dragon book, for all I know, might have a Pratt parser mentioned in some exercise to the reader somewhere. I almost
guarantee they do, but so they don't,
That's not the problem. The problem is not that the information doesn't exist. It's that it's not presented as the first way to understand it, is that you have left and right-leaning trees and you're trying to interleave them, which is the critical part, right?
Yeah. I'm looking in the P section really fast. Pratt VR, 189 to 90. Yeah, so they mention it for like 1 page.
Yeah.
In the Dragon book.
Yep.
Yeah, and it's like, yeah. In the references for chapter 3. So they don't even really talk about the algorithm. It's like references. Okay. So if this is about parsing, it's misleading because it's called compiling expressions. And that to me says like back-end stuff.
This is definitely back-end.
But there was a thing that said side note, it's just okay. Pratt parsers are a sort of oral tradition. No compiler or language book I've read teaches them. Okay, so he's talking about that paper here. It's the most elegant way I know to parse it. Why are we parsing expressions again in section 17?
That's really weird. No one would know to even look at this if you were just building a parser because you wouldn't be reading this part.
I mean, I guess, so I'm using it as a reference, right? But if you're using it as a learning book, you read it differently and you probably read the whole thing. So I don't know.
No, I object. I object again. Because this is exactly what happens with the Dragon book. You read the parsing part and you go, wow, this is really confusing. You may never get to the compiling part. You have to teach the parsing well, because without like solid understanding of how to build a parser and keep it that simple, they're never going to get to the part where they like, do optimization passes or whatever else, right? So like, no, this is the same problem as the Dragon Book again.
Yeah, I mean, I don't understand the motivation behind doing this later. Maybe we should ask him. Um,
Yeah.
it seems weird to me because he's like, oh, now we're, I guess, so it's called crafting interpreters, right? And an interpreter is a lighter weight thing than a compiler, where you
Right.
have some other program that's the runtime. Typically, you might even look just at the tree and like run plus by saying, oh, I'm visiting the binary tree and this node is plus, and so I'm going to add A and B or whatever, right? And then
Yeah.
compilers are when you take that several steps further such that you can create a program that could run on its own
Yeah.
without something else running it, right? That's the difference between an interpreter and a compiler. Um, I don't know why that, like, he's acting here like that causes you to change the parsing, which it doesn't.
Yeah, it's very
Like,
strange.
the parsing, the method of parsing is orthogonal. So I have to believe that this is more incidental. Like he felt like that was more advanced and wanted to leave it till later.
Possibly.
It's just weird. I don't get it. Okay. Um oh, but yeah, this is mostly parsing token. Why are we here again?
It's so weird to redo this. Like you'd think that this would have been in the first part, where
Maybe
about parsing.
maybe this was going to be a second book or something and it wasn't long
Maybe,
enough.
maybe this book is more of just a collection of things and that got loosely reorganized, and it wasn't
Oh.
ever designed as a book. Like I reshuffled my blog posts or whatever. Sometimes that can happen.
Okay, parsing prefix expressions, parsers for parentheses for grouping. I still don't really, I mean, I'm skimming again, obviously, but I still don't see the actual. Okay, here we go.
Here we go.
This is the actual part that explains it. It's
Yeah.
2/3 of the way down, section 17 about a compiler instead of interpreter.
17.5.
I mean, it's good. Again, this is
It's
good
disappeared.
information. I'm
Yeah.
glad it's here. I just don't quite understand.
Yeah.
Don't understand the order of the information. And
It
again,
needs to get moved up. Yeah.
it's not temporal in the order he learned it or anything, because he wrote that blog 10 years before this. So he knew this the whole time. So he's interleaving parsing with
And code gen.
output, which
Yeah.
again, it's a fun stunt, but like you don't want to do that once your compiler exceeds a certain complexity. But I mean, for teaching, I guess it's fun to show how simple it could be to
Right. Yeah.
emit code, right? Um, all right. There's a precedence table. Prec none for all these things. I don't know. Get rule. Okay. Yeah, so he's broken it into a couple of functions here, but and I don't know if these definitions are above or below. Advanced might be eating a token. Oh God, he's broken these into separate functions that you return because Java. All right, I'm not going to understand this.
Yeah. Yeah.
But so he returns a function from get rule. I don't know. I don't know. Get rule is later. This looks more complicated than it needs to be, honestly. But okay,
Like,
but he does talk about it and reference it. I can't evaluate just from a skim how good I think the explanation is, but the information is there. And
but
that's
once
great.
again, it's not. It doesn't look like it's explaining it in terms of like. I really liked your explanation of it in terms of like, look, we know that it's either going to be a tree that goes this way or a tree that goes that way, and all we have to do is like alternate between those to get the right thing. Here we go. That's a much easier way to understand how these algorithms work. And so again, I would say that needs to be kind of front and center, I think, in an explanation. because a lot of times these things are implicit, like they don't really like say what actually needs to happen for the algorithm, and
Yeah.
it leaves you wondering what the algorithm actually does,
Well, that's
right?
my
Like
big thing.
literally.
That's my beef about a lot of things, like technical writing generally. This book, by the way, is sort of, this book is, I do agree that I don't, while skimming, see the deep explanation that I would like, but maybe it's there and
Yeah,
I just,
maybe.
maybe
Yeah,
I'm
we'd
blind
have to
to it,
spend some
right?
more time with it. Yeah.
Yeah. Not a criticism of this at all, but more like when you read some of these computer science papers, right? There's like an academic computer science voice that people have learned to write in that is not very much like the voice of the great computer science papers, by the way. So,
Right. Right.
think about that. But it's a voice that involves trying to sound smart, but also not explaining things too much, and especially not explaining
The important part.
the reason you would do something and the context and when would you do this and when might it be a better idea to do something else, right? And like all of those, that's the real information. Like the algorithm, like if you have enough context and understanding of the problem, usually algorithms are not that hard, especially if you have like a hint at what it is. But like we seem to have all this writing that's the opposite, and that's what, there was this tweet that I deleted because I didn't want to harass people accidentally, but it was
We
about
should
that.
point out
It
before
was
you
about
mention
that
that tweet.
probabilistic algorithm book.
Before you mention that tweet, you should
Yeah.
point out that like this, thankfully, this crafting interpreters page seems to be written in a much
Yes. No,
nicer
absolutely.
fashion, which is nice. Like if you look at just what's on the screen right now, that's very human readable, right? Like no one's going to be like, "What the heck is he talking about?"
No.
They're like, "Oh, I get it," right? Like, okay,
Yeah.
I see what he's saying here. So that's very refreshing as well.
Oh, absolutely.
But
I'm
yes, sorry,
all in favor.
continue.
If you're ever going to explain something, make it more like this and less like whatever random computer science
The
paper.
GJK paper. That's
Yeah.
the ultimate reference of all time. Just read the
Yeah.
GJK paper, and if your paper sounds anything like that, delete the entire LaTeX file and make a new one.
Yeah. Um, yeah, okay. So the information's in there. Someone says Java is ast walk interp and C part is bytecode interp. I don't know what C part means. Oh, I guess this is in C. So they're redoing stuff in C. I don't know what Java looks like, but this looks like C to me. So yeah. Anyway,
Yeah.
the end. I think we're out of stuff to talk about, but it's just
Yes.
I wanted to do my part to signal boost several things. One, this is very simple. Don't First of all, if you understand it, don't get all high and mighty and try to confuse other people about it because it's actually pretty simple.
Yep.
Two, what do we do about this cultural problem that we have where if something as simple as this still, despite these other people having done what they can to publicize it, is still not understood by many people, right? What about the things that are actually more complicated, right? What about those? Um, I don't know, but
I mean, I think it's a fitness function problem, right? Like currently there is no reinforcement function for someone else was able to understand it. In fact, it's somewhat the opposite. Like for academic stuff, it's probably easier to generate more papers the less number of people understand what you're talking about because they're much less likely to reject it from a journal if they don't really know what you said exactly, right? Like if you understand something, you might realize it's not new.
yes,
But if you don't understand something and it just kind of sounds like it's roughly something, then
yeah,
you'll be like, "Oh yeah, you should publish that," right, or whatever. So I assume that part of the problem is that if literally just getting papers published is your fitness function, you're
yeah,
kind of it. This is what happens. So you just have to stop that. Like the whole idea of like peer-reviewed journals and all that has to go away. That was a very
yeah,
bad idea. It should never have happened. And what you should be doing is like, hey, if a particular publication is able to actually have other people be able to go do something with it, that is the actual fitness function. And how do we get there? How do we get more towards that, right?
yeah. I agree with that. I think one other thing that happens is a lot of so-called algorithms, right? Like especially as you get more applied in these papers that claim performance wins and stuff, which are usually almost never real.
garbage collection is faster than manual memory management.
Yeah, or even our tweak on
Yeah.
garbage collection improves it by
Yeah.
13%, and it
Yeah.
doesn't really, right? And it
Yeah.
also, by the way, has all these pathological cases and stuff and inputs.
Yeah.
We just wanted to get this paper out, so we didn't really
Yeah.
think about this other thing, right? And it's
Yeah.
like these papers are full of that stuff, and the more you understand what they're actually saying, the more you see those holes, right? Whereas if you don't really understand the algorithm and you're just like, oh yeah, it looks good, right? Um, Same thing, right? That feeds into that paper fitness function thing you were talking about, from a slightly different direction. So yeah, oh dude, I have so much beef about computer science papers that claim performance improvements. It's been
There's a lot of
sadness
issues.
every time.
Yeah, there's a lot of
Every
issues with
time.
that. Most computer science papers don't know how to measure things, so they're very suspicious usually.
Yeah.
But yeah.
Yeah. All right. So we have to bring back the meme because
Yeah, bring back the meme.
this is what the
Let's get
people
that up
want.
there.
This is what the people want.
This
All
is
right.
all. So the only takeaway that you really need from this stream is this meme.
Yes. This is about the entire intellectual content of this stream, honestly.
Can I
So,
make one? Can I make one change to this meme to make it even more awesome?
yes.
Can the dude in the cloak say that's left sometimes?
That
Just
might
to make
be too smart,
okay.
but yeah,
Okay,
let's do it. Here we go. So
because that makes it more specific to parsing, this particular parsing.
we
problem.
are a prompt service.
Because then it's like almost impossible to even understand the meme unless you've seen this stream. Because it won't make any sense otherwise.
So do we want to modify this? Or
And I think that was fine.
I'll put a 1. Must use Layler 1
Yeah.
generator with flex and Kubernetes.js with them.
I mean, there was a thing like, this is my only suggestion there. That's probably what you should put, but I remember the Red Dragon edition of the book having some garbage on the front, like LALR1 parser generator and syntax-directed translation. Can you just copy what it said and stick it at the top there? Because that is pretty close to perfect as well.
Okay. Syntax-directed translation to defeat the complexity of compiler design. That's literally what it says. It says,
okay.
So the dragon, this is the new version, but it's in principle, it's like when Disney remakes The Lion King in live action. So all the elements of the scene are the same. The dragon is wearing a shirt that says complexity of compiler design. And the sword, you can't really see it, but the sword is the sword of Layler parser generator.
You got to get that in there.
And the shield of syntax-directed translation, right?
Yes.
All of which is bullshit. The one phrase on here that isn't bullshit is complexity of compiler design.
Which is true.
Which is true, but parsing isn't the complicated part. It's the rest of it that's hard. So, syntax-directed translation. With Layler parser generator.
Yes.
It might be a little small, but
yeah. Well, what can you do? Memes
This is the complexity of memes. All right. I don't know. I think this is as high reg as it goes.
Yep.
All right. See, we are a full service shop here. Yeah. Okay. Very low res.
Oh, it went off the top.
No, it didn't.
Oh, I can't see it. I can't see the top of the meme.
Am I? So my OBS may not be.
Oh, okay.
No, it is. Maybe it's Google is not showing you.
It could be Google is Googling it. As long as it's visible in the real meme, I'm fine with it. Oh, now I can see it. It was just the zoom, I guess, was making me not see it.
Well, the zoom in
was
cutting off the bottom for me. So.
Okay.
Yeah. Okay, so that's great. Thanks everybody. We could do questions or something if you want to hang out. Otherwise, that's all I want to talk about.
Totally up to you.
Does anyone have intelligent questions that is worth the time of Casey Muratori when he could be off making new things for his Substack?
Gallivanting.
Yeah, or gallivanting, or doing both of those things simultaneously. Serious questions. Oh, someone is saying the crafting interpreter book was in two parts. Part one was in Java and part two was in C. And so maybe that corresponds to the interpreter and compiler parts. But then online, it's all smushed together now. That makes more sense.
I do think it feels like when we were looking at it, I was like, this kind of feels like a thing that was like, it was written in various ways and then, assembled. And that kind of thing always has some rough edges there. Like Mike Abrash's books were that way, right? Like they were like, hey, these were a series of articles and then we kind of reworked them for a book and whatever. So you kind of there's a little bit of things where it's like, wait, why is this here or in this spot? And it's like, well,
Yeah.
we're not going to rewrite the entire thing to make it flow correctly. So,
Yes. So here's a question. Are parenthesized expressions ever done in parse leaf in my example? So we did sort of skip. I mean, it's essentially the same as some of these other cases we talked about of more complex syntax. It's essentially the same as the for loop, right? So here's the thing. When you're going to parse an expression, I've got so many versions of this function.
yeah.
Like when you're going to parse an expression, you parse a leaf here. And parse leaf, I talked about in the very beginning and just ignored it after because it's not the point. But when you're here, what this is just looking at the next token and deciding what is your value. And if instead of a 3 you see an open parenthesis, then right here you just say if it's an open parenthesis, return. It's not really a leaf because it's a sub-expression, but you just go in, right? Now, the way that I do unary operators, I skipped over unary operators because it's not really worth bothering, but I just handle them here as well. I just say, if this is a unary operator, then call the parse expression with the precedence of that unary operator. And there you go. Oh, that is one interesting change or difference between the old version of the parser and the new one, besides getting rid of the tree changing code, is before I had unary operator precedences for some reason, although they didn't really do anything. And I had binary operator precedences, but they weren't even on the same scale because they didn't interact, right?
So you unified them.
Yes. And so now they're on the same ruler. And so when you're doing things this generally, if you don't pass in the correct precedence from here, you'll mess up your unary versus binary precedence. But basically things either go here or in the parse binary, and it's like your entire grammar, Okay. What about parsing each binary operator along with its right operand and then just inserting that where it fits and then link?
Isn't that sort of what this is doing?
Paste bin. Parse unary. Okay. While token is binary op. Parse unary. This is sort of like the tree changing thing I was talking about. This is like a very compact version of it because you're parsing it and then you're changing the links, right? If I'm reading this correctly. Yeah. So hybrid approaches between these two things, I think, could work. I'm not sure why you would do that. I'm not thinking that hard about you're starting at the root.
Sorry, go ahead.
Well, it's like I don't know. Maybe this is just another way of writing the same loop, but with
It is like it
yeah.
basically this is the unrecursive version of the thing, right? You
Okay.
you keep building right leaning trees, or I should
Yeah.
say, you keep using the right slot.
Yeah.
You walk down the right side
Yeah.
until you need to walk down the left side.
But the only thing that's sus. So I guess when this says parse unary, I was assuming that that meant like a unary operator or a leaf, but I guess it means an increasing precedence run, like I was talking about, because otherwise, why would you ever need to cursor more than one step or whatever? You know, that's what's confusing me about this. Um, I don't know. Anyway, why not do it this way? I mean, sure. Like, if this works, that's great. It's not really in principle different. Um, the core idea, again, to put it in the bell curve meme way, the core idea was just that, the default tree making that you would do is right in some cases already. And then
Well,
just use that to construct the thing, right?
I would say there's one reason, like, again, I don't write parsers, so I'm just going off of what I've heard so far. But
Yeah.
one thing that doesn't look great about this is effectively this gets worse the more you have to do that inner while loop.
Yeah, well
So in the
that's
one,
very sus. I would never do that, right?
right? So like in the one that John wrote, because you're building it kind of in order from the bottom up, you don't have that problem. You're always just going to the right or going to the left, and you're just doing one step
Yeah.
ever.
Yeah.
This version's like, well, now every time I get a new one in, I have to chase down to find where I would have been when I inserted it in John's version. So it's kind of it by flipping those two, it
Yeah.
feels worse. Like it feels like this is going to be like an n squared kind of a thing that could happen if you construct a adversarial input sort of thing. I could be wrong about
Yeah.
that. I don't know if the
Honestly,
person in
my
chat wants,
brain's tired,
right?
so I'm not thinking that hard
Okay.
about it. But
That's my
uh,
only thought. Does
but
that
yeah, I mean
that
this while
sound right?
loop, I don't like how that looks, which I
Yeah.
think is a summary of what you just said. Um,
Yeah.
here's the thing. Another thing about computer school is they teach you to make trees all the time, and that navigating trees is cool and fun. Trees are really bad, and I want to at some point try to figure out a way to make a version of our compiler that does not use trees. It's difficult because they are in principle trees, in the sense that like any recursive data structure is kind of a tree, sort of, I guess, because you're referring to some other part that may be small or it may be quite large. Um,
I assume that RPN kind of the existence of RPN means somewhat implicitly that expressions anyway never need to be represented as a tree. You can
yeah,
just do them, right? Like you could easily make a compiler if it only ever dealt with expressions. You would never have to have a tree to get the right answer anyway. You might want a tree for other reasons. But.
yes, yes. So anyway, the thing about like trees are bad for two reasons, and I think we talked about this a little bit before, maybe, but all my experience since then keeps like if I had time, I wish I had time to think about it, right?
Yeah.
The nodes are really big. Like the tree for this thing, or let's take something simpler, like this is like node for the equal, node for this, node for this, node for the unary operator. Maybe we don't have statement nodes, but some people would. And like it's like
Right.
5 nodes, and they all have like probably the base node that describes where they are in the program, so you can do error reporting and all that, and like probably some stuff that helps link it to the later results of compilation, right? And so like I don't know how big our base node is, but it's like 100 bytes. I don't know. It's like it's stupid, right? And so imagine this was 500 characters long instead of like 12 or whatever it is, 11. Let me actually count 4, 8, 9, 10, 12. I got it right. So that's a factor of 50 bigger than your source text, and that's kind of dumb. It just is.
Yeah.
And I mean, Casey probably knows. Like, I'm not the most hardcore person about optimization because I more prefer making functionality work. But like, I don't do stupid slow crap, and I don't make things way bigger than they need to be if it's important. And like, this is really important because we instantiate like millions of these nodes, right? And it's hard to make them smaller while it's still, I mean, there's things I could do to reduce a small number of bytes at great effort, right? And so Yeah, I just want to re-envision it at some point as something that doesn't use trees. So the other thing about trees is like this looks like a cheap operation, right? But you're going to things that might be distant in memory. Now, that's less bad here in the middle of a parser because you probably just parsed this stuff recently. And if your allocator is not like returning an address that's like rand mod size of address space, you know, then that probably has better behavior, right? If it gives you nodes that are next to each other. But you're still, I mean,
It's
for,
still n squared, right? It's n squared in
yeah,
the length of an expression. Am I wrong about that, chat? Like the main problem I see with doing it backwards like this is just that it's n squared. Unless I'm misreading you, maybe I can't see the chat right now, so because I
yeah,
wasn't, but I
I'm
don't know what
looking,
they think. But that's my gut feeling is that like you wouldn't do it this way because it's n squared for no
yeah,
reason, like no real benefit. If there was a benefit to it, maybe you'd say, well, I'll eat the n squared because I know that my language, I'm not trying to make a language where you can have expressions that are 1,000 elements long or
yeah,
something, which is fine. But it seems like a bad decision
yeah.
unless you got something from it.
There's something someone's saying that I want to address about this because this is a common, uh, people who know a little bit of optimization stuff, modern things say this. And I want to push back on it just again, to spread the knowledge. So someone is saying, someone said, hey, allocating every time you want to create a node will slow everything down. And someone else is saying, you're assuming he's doing malloc every time. He could just be doing bump allocation. And actually, I don't see the rest of the context of the conversation because there's a lot going on. So maybe that wasn't directly in reference to this. But if what is meant is it's not that bad to do this or even make a tree because you're not actually calling malloc. It's like, okay, yes, it's good that you're not calling malloc for every node. That's great. That is a good step to take to make your program faster. It does not really fundamentally solve certain classes of problems. You're still visiting memory that may not be next to each other. Because the reason you have a tree, by the way, right? In the start, we were all doing left leaning trees and right leaning trees, which are pretty linear. And so if you have something like that that's really long and it's all allocated in memory from the leaf up or the root down or whatever, um, actually in our case that wouldn't have been true because like the left child was allocated and then we did all the sub stuff and then we came back. Like things may not end up being very close to each other in memory, actually, depending on the size of the tree. But the whole reason you have a tree is because the shapes can get more complex. And then you navigate that more complex shape. And anytime you navigate a more complex shape than that, you're crossing, like any link between nodes is a link between things that may be getting further and further apart in time, right? And so on the one hand, maybe that's a fundamental part of the problem. But on the other hand, you don't want to do it more than you have to. And this looks like more than you have to me, right? That's what
Well,
I'm
also,
saying.
can we bring up the that's tangential to that? Can we bring up the meme
Yeah.
again?
Okay, which one? Version 1 or version 2? Version
It
2?
doesn't matter because I just need the visual reference.
Okay.
Yeah. So the other thing that you could think about with this meme here is that like on the guy who on the left would be saying like just call malloc, and then the guy in the middle would be like you could be using a bump allocator, right?
Yeah, yeah.
And then the guy on the right is like, but what about the page faults? Because actually, when you parse something like this, even if you're using a bump allocator, if your nodes are all huge, you will
Yeah.
page fault all over the place and it's bad, right? Like there's compilers have this really bad problem that a lot of programs don't have, which is that at startup, they don't have any memory because why would they,
Yes.
right? You're just cold calling them off of the command line. This is
Yeah.
just how we have unfortunately designed the execution environment of modern computing and not much you can do about it. People
Yeah.
expect to be able to call a compiler from command line. When you do that, the compiler doesn't have any memory provisioned. And so every extra byte you use is like, well, I should say every extra 4K you use on something like Windows is another page fault waiting to happen,
Yeah.
which slows down the runtime of your parser. So you actually do care about the size of things. Even if you're using a bump allocator and think you're not paying very much for allocation, you probably actually are in this particular case.
Yeah, I told Casey this before, and I think it sparked some of the experiments he did. But
It did, actually.
last time we measured it, which was a while ago, and we haven't measured it again since then, but like 12% of our runtime was just getting memory from the operating system. Like, it was a lot, like 12%. When you're trying to speed something up, if you could make it 12% faster,
you're really happy if it's already fast.
Yeah, if it was already a reasonable program.
Yeah.
And so, yeah, it's just, these things are problems.
Yeah.
Someone says, in a compiler I'm working on, I noticed in my code that I only do depth first traversal. So I just linearized the tree into an array of nodes in depth first order.
That's what you do too, John, isn't it? Sort of in your compiler?
Kind of. Yeah.
Okay.
I mean, I still have the nodes. I still have the tree structure, and sometimes I need to ask, what's the child doing right now? But I do linearize the nodes. It's for a little bit of a different purpose, which is about being able to stop compilation and resume, because an identifier isn't ready or something. Now that said, the thing I've been thinking lately is I do that. I used to do it just by literally linearizing the nodes, like having a big array of all the pointers. And then I was like, that's kind of maybe too dumb. And you can imagine pathological cases where you just allocate a giant ass array that is not helpful. So I went to something that's a little bit more of like a stack thing where you push something on and then it expands its children onto the stack and then you visit them. So it has a much smaller memory footprint and it's way slower. So, but it took like a painful week of stuff to do that conversion because a lot of the compiler is about what can we compile right now. And it's all intimately related to that structure.
Yeah.
Actually, and then there's other systems, like while you have that information, there's other systems that were using it, and it was just really, I was supposed to be enjoying a vacation in Hawaii and I was actually, no, that wasn't quite what this was, but so I want to go back to maybe something that's more linearized, but the real observation to make is, maybe a lot of things are guaranteed to actually compile if you have the leaves, right? So the main thing that might not be ready to compile is an identifier, right? That just refers to something in your program. A struct dereference, right? A dot operator. Similarly, you might not know the struct yet. But beyond that, it's like, what's the problem really? And so you could imagine linearizing only those things. And then because identifiers just look at this, right? How many times do we use the word next here? The way we do it and the way basically everybody does it, that's 6 different identifiers with the word next in it. And the way I linearize my thing, those are at arbitrary positions throughout this array among the other nodes because it's just I walk the tree and get the leaves and put them in, right? If you just were saying these are the identifiers we need before we can proceed, because that's the thing you're most common to block on. And then if you're only worried about those, you could have a much tighter loop that's just like looking up names and only concerned with those data structures. Then you might notice that you asked for the same thing 6 times because it's much closer together. And you're like, oh yeah, there only needs to be one, right? So there's probably a lot of efficiencies that could happen that way, but it's a large structural change. And so I just haven't wanted to do it yet. Someday. Braid Anniversary Edition is coming out on April 30th. And part of the reason it is coming out at that time is that I'm not rewriting the core of the compiler at all. Do you store additional for later phases in syntax tree? What's your opinion on having multiple internal representations for different compilation steps? This is something so I'm very contrarian by nature. So when I do something, I tend to do the opposite of the Dragon book, right? Or whatever. And compiler education loves making a new representation for your program to do a pass on it, right? Like, hey, we've got our syntax tree. Now we're going to make a control flow graph so that you can decide where the program goes or whatever. And then we'll make a different thing out of that and all this. And actually one of the, God, I'm blanking on his name because again, I'm old. Cliff Click, who runs a coffee compiler club stream I think it's mostly for his. It's sort of for anyone who wants to talk about compilers, but it ends up the more motivated people doing the most work end up being the topic of conversation, and so it's usually his compiler, right? Um, but he actually, again, there's this weird thing where really good basic points sometimes get conflated with other things. So he has a paper called Sea of Nodes, which is about a different representation that's not exactly as tree-like, I guess. It's still nodes, right? Maybe it is a tree. I don't even remember.
Well, it's a C according to the title.
But it's not. It's not a more extremely hierarchical thing. But the actual very good takeaway to take from that, even if you don't want to use that representation, is that when you're going to compute something like, to do control flow or data flow analysis, you need to know some things like what code could branch to this point, right? Where can we go after this, right? And that makes up the control flow graph. And the data flow graph is like that for, value numbers or whatever your representation is of what variables could be, right? And all of the way this is always taught is you start with a syntax tree that just exists. It's just out in the ether. It is a primordial syntax tree. And then you traverse the syntax tree and you do analysis on it to build these other graphs. And the point is that's really stupid because, for example, actually I said syntax tree, but often it's later. Often it's like semantic. You've done like some type checking and stuff, so you know what the things are, right? But it's still in a tree. I tend to conflate these. To go back to the original question for a second, because we do literally put everything on the syntax tree node. All the later information of compilation goes on there as well. There's some ways in which that's bad. Actually, to finish answering that part of the question, I guess I just did. Like, the reason I did that is because I just wanted to be the polar. Like, I didn't want 17 different trees. A, that's complicated. B, it's really slow. You're copying all your data all these times. And I'm like, I want my compiler to be fast. So we're just going to do as little as we have to do the work, right? Like that should be for a modern programmer who wants to be way better than the average programmer in 2024. The heuristic you should have is that you do what you need in order. You need to have a clear picture of the problem, which sometimes is very difficult. And then you just do as little as you need to solve that specific problem. That should be your first step. Then once you have that program, you might analyze the performance and say, oh, if you realize it's going to be slow, don't do it that way. But if you didn't realize, and then you run it on some real world data, you have some information that helps you make it better, that's all great. But like, there's this cult of complexity in the education system for computer science. It's just like, fuck yeah, dude, 17 trees. It's awesome, right? You're being a computer scientist when you make all these trees. And it's actually...
I think the thing is, John, on the cover of the compiler book there, where it shows where it helpfully has the different words on the various parts of the metaphor, so that you're not confused about what the metaphor is. A lot of people don't know this, but because you can't see it, but on the knight's underwear underneath his armor, it does say shit ton of intermediate representations. That's another tool that they use in that book to slay the dragon of compiler complexity.
Of complexity, yes.
It's by having like 12 different IRs.
Yeah.
For every possible thing you might do.
But okay, so to get back to the point that Cliff makes very well, which is an important point, which also needs to be signal boosted. Just in the same way we said parsing precedence is simple, a lot of stuff about compilers is simple. And again, it's important because some of it's really complicated and hard. So we need to identify the simple things and just understand how simple they are. So all this construction of control flow graphs and data flow graphs and the algorithms they give you are only necessary because you didn't have any information about this tree that you got at the start, because that's how the algorithm's written. In reality, and we do this actually, when we do our control flow representation, it's not really a graph, it's like an array of like some values, right? Like for example, you have a for loop, right? This comes through in our compiler, it's one node. You've got a child that's like the condition, right? And then the then block and the else block, and then maybe some other modifiers are on this node. And we've done all the type checking. So we know the variables are valid. We know what type they are. We actually do some more complex things where we allow you to overload for loops for data structures, right? And so we know if that's happening or not. Then it's time to output the code. And what does that look like? Actually, let's take an if statement. If statement is even simpler. It's the simplest one. Sorry. If statement. So you parse it. Keyword if. In C, there's parens, whatever. You parse those. There's a condition child, and then there's a then block. Sorry, I said then block and else block for the for loop. It's like I've been playing too many video games. For loop, sorry. We don't do else blocks. Python does or whatever. We just have a body of the for loop. For if statement, condition, then block, else block. We know everything about them. And then it's time to start generating code, which is what you need control flow and data flow information for, right? You actually don't really need data flow information unless you're going to optimize, or control flow information. This is all only about optimization, which I don't even know if they really tell you that in that book. Okay.
You sort of need control flow information just to generate the code at all, though, right?
Not really.
I mean, you need jumps and stuff. I mean, you need
to know the jump target.
Yeah.
Yeah.
But I mean,
that's not
flow,
control
right?
flow, because that exists in an isolation. Like,
okay.
Yeah. Anyway, so my point is just the point that Cliff makes, which is very simple, is you've got what's called a basic block in compilers. This is another concept that I wouldn't really argue with. A basic block is just some statements where if any of them are going to run, they're all going to run because there's no branches or whatever. Actually, there's different kind of... Sometimes you could branch out of a basic block and you call that a basic block. Sometimes you have a minimal basic block versus a whatever basic... I don't know. Anyway, for mine, again, in the pursuit of simplicity, a basic block for me is you can't branch into the middle anywhere, but you could leave if you want. You could leave early, right? Okay. You're generating your bytecode or whatever representation for your if statement. You're going to output the condition no matter what, because you can't do anything until you know. So that's in your same basic block as whatever the code was before the if statement. You start outputting the condition, and then you're going to branch somewhere, right? And you're going to branch to the then block or the else block. Instead of just making some tree and then later running analysis on the tree, you know, because it's an if statement, okay, we're about to make two new blocks, the then block and the else block. Okay, those are basic blocks. I think in C, isn't this block in C the term for like a curly brace and whatever?
I think so.
It could be confusing. This is just basic block means a very specific thing in compiler stuff. A block in C could be composed of many basic blocks, right? So you have a then block, you have an else block. So you do the condition, and then how do you write this? If you're writing your own pseudo machine code, it's like, well, if the condition is true, well, if it's false, we jump over the then block to the else block, right? And then at the bottom of the then block, we jump over the else block to like whatever's afterward, right? And so because you're not allowed to jump into a basic block, when you make a then block, that's a new basic block from the one that had the condition in it. And when you make the else block, that's a new basic block. But you know what the parent is, and any childs of these blocks are going to be determined by recursive code generation. And so like there is no analysis step to create the tree is the point. Like, or whatever your representation is. At every step, right, because you know the functionality of the node, you just do it. You just say, oh, add these to the successor list because we created the blocks when we're processing the if statement. So all these algorithms for like walking over a tree to do this and to find like the dominating, well, I don't know, maybe dominating frontier still exists. But most of the creation of the thing is literally just the code that you would type to record something in the data structure of your choice. Like that is literally what it is. It's insane, right? And people just write tons of papers and books about it. It's nutballs. Again, it's actually very similar to a thing, one of my game developer articles that I wrote, which was after I got fed up with all the terrain LOD stuff that I was doing, which was some of my earliest experience with being disappointed in computer science papers that promise performance, good performance. I decided to think about like, hey, let's do LOD for terrain as static meshes, right? Oh, but you have to chop the meshes because the faraway pieces need to be lower res and stuff. And oh, that's a hard problem to know how to stitch those together. You got to have heuristics. Everybody at GDC was telling me that, or not everybody, the few people I talked to, they were like, oh yeah, you would need a weird heuristic to whatever. And I'm like, wait a minute, you had the input mesh and then you chopped it. You like know what polygons go together. And then as you reduce the LOD on the other side, you know the source polygons, right? That generate, you know, like LOD means you turn fine detail into coarse detail. So if you have two triangles and you realize you could make them one triangle, then you actually know that information. And so if you wanted to maintain a seam between those two things of different LODs, you actually can do it perfectly with no heuristic because you made the lower detail representation. So you just say, oh, here's the high res seam. These two triangles collapse into one. They had edges on that seam, so make those two edges into like, you know, one thing. And it was very simple, and that was all it was. And it's like the same thing in compilers. It's kind of astonishing. Sorry, that was a long explanation that nobody cares about and nobody understands because I'm tired and rambling. So it's what happens when I play video games and then sleep for 6 hours. Let's take a couple more.
It wasn't video games.
A video game.
It was a very specific singular video game.
A stress testing simulator. Someone is saying, is it a bad idea to use the correct grammar for operator precedence? Okay, first of all, I'm inclined to ignore this question. I won't, but I'm inclined to ignore the question because you were saying correct grammar, which is like some kind of Harvard shit to say, right? Like, yes, there is this Backus-Naur form, for example. It's the most popular way of representing this kind of grammar for a programming language. What do you mean by correct? Okay. Why are you elevating that to some? It may or may not be a useful way to represent things. For me, I have never written this out. This is, you know, what these are is in like a sort of a pseudo kind of mathy but kind of programming language form. These are like what the things are in your language. I've literally never written that for this compiler. So I don't care about this kind of representation. So I object to the word correct. It's like when people say they're making their C++ code const correct. I'm like, the word correct there is a propaganda word. It is not describing anything technical. But okay. So yeah, I mean, the problem is this is just going to be really slow. Like you're writing a buttload of if statements and okay, I mean, you can do that, right? You're gonna take lots of branch prediction failures, and even if you don't, it's just a lot of instructions that you don't need.
I mean, isn't this also basically like the even more expanded version of what we read in that Contrasting Interpreters book? Like, this is basically that. It's that exact code, but you just expanded it out.
Well, it's also in the opposite order. So we have compare here and then add here. So you go up the file as the precedence goes up, right? But like I said, I mean, if you miss that part, don't do this. It's not the right way to do it.
I would say also one thing that I find just personally as more of a consumer of this information than a producer is I find BNF form to be kind of useless for me to understand what the heck actually happens in a programming language. Like, if you present me the BNF for as much of C++ as you can write it for, which is not all of it.
Yes.
It doesn't really help me. No, like I can't really like some things are fairly clear. Like it's like, oh, okay, if I just read like multiply expression, I can sort of understand what the BNF does there. But like go to like type declaration and I'm like, I have no idea how this helps me. Like by the time I finish like going through and going like, okay, so the consts could have gone in either order around, wait, what's this thing again? Oh, it's this, because you constantly have to introduce non-terminals
Yeah.
to explain what's going on in the BNF. That's sort of how they work. And non-terminals are, by their definition, things which oftentimes don't exist in the actual programming language. Like they don't have an actual like thing a human would read. They're an artificial category of thing, which you then have to learn what it is. So one problem I have with BNS generally is when people try to use that as the way to formally define a programming language, while that may be fine for ingesting into various tools of some kind, if that's really your thing,
Yeah.
that's fine. But as something that humans work with, I don't find them to be very good.
Yeah,
Um,
if I'm going to learn a new programming language, I don't want to see that at all,
I
right?
don't want to see it at all.
Um,
Yeah.
the one thing that you could say it's useful for is like after I've designed my language and it's kind of done, I want to analyze my grammar to make sure I didn't like do something stupid, like maybe there's a weird. See, this is a very hype. This is what people say, I guess. Like last time I argued with somebody who's very argumentative that who I haven't spoken to in years at this point. He was making this argument.
I know who it is.
Yes, and but it's just a very hypothetical case because, like, look, if there's a weird so one thing that the whole thing we were saying before about there's a shift reduce conflict or whatever, right? The BNF of the language, and then going through this kind of process of breaking it down into token by token and then analyzing like what is the scope of all things that could happen next, right? Is an analysis you can do with that representation. And then you could print or essentially a shift reduce conflict report or whatever of like these are the weird things in your grammar. But the thing is, in reality, that's never going to be a problem because if you used your programming language at all, you would notice that you tried to type something and it didn't come out the way you wanted, and then you would change it. And so it's like it's an academic solution to a non-problem in a sense. Like if the destruction of the earth was at stake and I was like, I need to make really sure that I didn't make a weird mistake here, I would totally go do that, right? But like that's just not how things are,
I
you
also
know?
don't know how useful even it is in the case where the Earth is about to be destroyed, which of course happens often. Um, and that is that it doesn't really tell you much about the part that you're likely to actually have problems with, which is the rest of the compiler. So it's like having this like extremely formal description that leaves out basically any semantic checking at all. And then the explanation for, well, how do we do the semantic like what's the notation for the semantic checking part? They're like, well, we don't have that.
Mm-hmm.
Is not like that doesn't help. Like that's just like you made this artificial thing that we have to then go learn as a separate exercise that actually doesn't capture most of the problem. So what was the point? Like
Yeah.
if you got to the point where you could describe the entire correctness of a programming language in some kind of really concise notation, then that's maybe more interesting. And maybe some theoretical CS people have actually done that, but that's
Yeah.
not BNF. So
No, I mean,
BNF is kind of frustrating to me most
I
of the time.
I don't see, yeah, like I said, I don't see much of the point in BNF except to prove that you went to computer school. Um, I have much more sympathy for the people who are trying to do like program prover systems.
Yeah, and that's
However,
more interesting.
I also think that those are a little impractical at the current time unless we make
Yeah.
some big breakthrough. But at least that makes sense to me. I'm like, okay, I get it. Yes, it is very hard for me to know if my program is correct. In fact, actually, no, it's easy for me to know that it's not correct. It's got problems. I just don't know what the problems are. Okay.
Right. Yeah.
Um, so I'm very sympathetic to that initiative, which the BNF is like maybe more of a cargo cult version of that. But like here's the thing. All that stuff goes way back into the 70s and the 60s and maybe even the 50s when like it was like maybe computer language is a little bit like human language, right? And you had all these cognitive scientists like trying to do grammar for English and stuff, like whatever. Like all that stuff is kind of mixed together. And again, I don't put the fault on any of the people who came up with these ideas, right? I do put the fault on our system, both academic and industrial, to the extent it participates in this, of propagating these weird, incorrect notions of what you should be doing, right? That's the part that failed. Having different ideas about how to represent your grammar is great. Like, there might be some cool ones that nobody's thought of, and it would be good to add those to the world if they have something to add. But after that, there needs to be some diligent step of the collective intelligence wherein we decide correctly and accurately what is really the good way to do things. And we've been pretty bad at that, as far as I can tell.
Yeah, it's piss poor.
Yeah. Here's a concrete question. How do you parse? So someone is asking about dot. We talked about dot struct dereferences before. There's a couple of constructs we have. We have like a dot b. That's a struct dereference, just like in C. And then our struct literals, because we allow you to use them as an expression and like infer the type and stuff. And I didn't want to worry about weird parsing ambiguities for now. We put a dot in front of our brace. So if you have a struct type and, you know, you could have your elements in here, you know, and they could be different types or whatever. And they're just asking.
Sorry, what does that do?
So if this is a struct, right, then this is a value copy of that struct with the fields filled in by these values. And you could use names if you want here. You could say like name equals hello, and these could be out of order if you specify whatever.
S is a type name or an identifier?
Those are the same thing.
Okay, so
it's an identifier that has to be evaluatable as a constant, and it has to refer to a type.
Right. Okay. So it could be something that's just referring to a type, or it could be an actual type name, but it just has to be something that can be. You can get a list of fields from it.
Yes, the compiler knows what struct this is at compile time, is the point, right?
Got it.
It could be a more complex, like we have compile time executions, you could run some stuff, right?
Right.
Whatever. So they're just asking, how do you know the difference? And the answer is just when you see a dot. So we have dot in our binary operator parsing, but when we see a dot, we just look one token ahead and we say, is there a brace? It's very simple, right? If there's a brace, it's this. Otherwise, parse an expression. Because this, like open brace, whatever, close brace is not really an expression in the way that we have this programmed. As Casey was saying before, you could play games about what's an expression and what's not. And, you know, I just chose not to do that for this. So this is a very, just like the for loop example we were talking about where you have specialized parsing, that's exactly what this is. It's like we go into a special mode that does this thing, and then we return that back out. And that's sort of here's the interesting thing is in designing your grammar. So I put the dot here just to make it easy. I don't know, you could maybe say that, but then as you're developing a language, you have to deal with, like you're kind of asking for it at some point. Like, oh, now this kind of expression looks like that kind of expression, and it's not clear which is which, and you have maybe if it is clear to the programmer, you have to do more work to like make the code look more ahead to determine which one it is or whatever. But the thing is, you don't really want to be playing that game anyway. Like you want people to be able to just look at the program and know what it means, right? And the more there's a parallelism where the more that you have to make the parser do crazy stuff to look ahead to determine maybe this is something weird, someone looking at the code may not understand that either, right? And so you just want things to be simple to read and simple to understand, and that tends to correspond to simple grammars. That's actually why, for example, so C has, putting this dot here is a kind of a defensive grammar design where it's like, I just like it better if it's clear. C has that in like, if statements and, they have parentheses around them. Why? Well, because sometimes what's inside the parentheses might look like if there's a unary operator afterward, because you don't have to put braces afterward. If there's a unary operator and you have an expression inside the parentheses, and the parentheses weren't there, it might look like a binary operator. And we're just going to say, screw it, there's parentheses. And that's how we solve this problem. And sometimes you do that. Sometimes people get on my case that they wish there was a little less punctuation, but I'm like, we could look at that later. In the meantime, I just want it to be very clear what everything is. And I don't want these weird problems. And I don't want people to be writing code. We exactly had we don't have that many unary operators that you tend to use in that case. We don't have the parentheses, which is why I'm saying all this. There was one unary operator that was causing problems, and we just changed it to a post order unary operator, and then that problem goes away. Okay. Do you do something crazy in the Lexer to maximize throughput? No, like Lexer is just really fast. I don't like the parser is really fast and it's way slower than the Lexer. One thing we do, like we don't allocate a trillion tokens, right? We reuse. There's like, some number of tokens that we're allowed to look ahead, and there's just like a ring buffer of them, right? And so we're not allocating, we're especially not calling malloc per token, but we're not actually allocating new tokens. We are allocating subdata of tokens. So if you have an identifier, we need to know the name of the identifier. We just make that little string somewhere that's cheap to allocate and point at it. Shout out to Coffee Compiler Club, by the way. They could use more viewership. It is a niche topic, but they're on YouTube. Let's find a YouTube video, since they tend to be pretty long and in depth. Updated 7 days ago. Yeah, they're still doing it. I wasn't sure, but yeah, they just talk about compiler stuff every week. It is invite only to be on the thing. So probably no bozos, but if you want to watch them, it's pretty easy. It's just, as you can see, it's a niche topic, like 300 views, 400 views. Yeah. Some of them, I guess, get more. Yeah, we'll post this on YouTube. Are you bored, Casey? Do you want to cut it here, or do you want to keep going? What's your level of interest?
I mean, I'm happy to do whatever you're up for. It sounds like if there's more interesting questions, that's fine with me.
Let's do a few
I don't have
more.
much to add, right? I'm only here to ask questions.
You're not in the middle of doing these things. I will say that starting, I think I didn't have enough breakfast, and I have a lack of sugar to the brain, which is why I started munching truffles.
Yeah.
So I feel like a couple of the answers that I've been giving in the past Q&As for 15, 20 minutes were a little too meandering and a little too not quite the best answer, but
maybe that's the end then.
Let's see if there's good questions.
Okay.
Yeah, that's the thing, is I don't want to put bad answers to questions out there. So I saw, as I'm scrolling through the chat, Oxford comma correct was something that somebody said.
Yeah.
What if you develop things that work with various languages, so you need not one parser but a dozen? Do you think writing them individually is better anyway, as opposed to using parser generator? Yes, but also if you find yourself using a dozen programming languages, you're doing something super, super, super wrong.
Well, making a dozen. An editor might be an example, though. Like I'm making making Sublime. I'm the author of Sublime, and everyone's like, I want syntax highlighting for Squeemalang. And you're like, I don't even know what Squeemalang is, but now I'm pulling up the web page for that.
Yeah.
What do you do in those cases? And probably a parser generator would be great, but the problem is usually that they don't work very well. The problem is not that it wouldn't be great if there was some magic way to make parsers quickly. The problem is there isn't.
Well, there isn't. So this is one thing that I wanted to say before too, because our parser right now is 6,000 lines. I'm pretty sure if we used a parser generator, it would be longer substantially, right? Because you have to do all this interfacing with the thing. And then you have to do all this making your own structure to cope that the structure of the thing isn't what you wanted. And it just, I've done it enough times to know. But here's the other thing. Like we talked before about how error messages are important, right? doing syntax highlighting correctly is, while somebody's in the middle of typing stuff that is not complete, right, is sort of equivalent to generating a good error message. Like there's a way in which those problems are very similar, where I don't want my highlighting to get all freaking stupid just because, I don't know, you
Just
like
reduce
forgot a
conflict.
parenthesis somewhere or whatever. Yes. But that's the thing, is if you use a parser generator, that is what you will get out of it, right? And then you could add some code when you see a conflict to like try to do something, but you don't have, because this is the thing. When you write the code yourself in recursive descent form, which I will say once again is too complicated of a name, you're just calling functions that parse the things. They should call it calling functions that parse the things parser. Okay? That is what it is. When you do that, you know exactly what you're doing. You have all the context, right? Um, it's just much easier to give high quality responses. And I mean, I have not made an editor that does syntax highlighting, but if I were to, I would absolutely do the grammars. I mean, if you like, there's this whole question. Okay, what if you're releasing the editor for everybody, and you want to provide a way for people to contribute and stuff? And even then, is the contribution like just them being able to make some code that simply parses the thing, or do they have to learn some weird ass, parser generator thing? And what,
Well,
I just,
I would also point out that like it's worse, I think, even than you're making it out to be, John, and you're already making it out to be bad.
yes,
Which is that like in a lot of circumstances that I can think of where you're trying to ship something that uses multiple parsers, they are, like you pointed out, working on something that's under construction. They're like, some kind of like checking tools or syntax highlighting or things like this. And if you take the example of like syntax highlighting, there is no way to parse a file for syntax highlighting. Oftentimes, there's things like pound if blocks in it,
oh yeah,
right?
yeah, yeah,
And or like stuff like that. And it's like, well, technically, there is a particular way that you parse that, which is you find out what the pound defines are, and you actually evaluate the if blocks, and that's the parse of the file. That's what the compiler will use. But that's not the best thing to show the view. Like the user would like to see as close as possible as you can figure out what a human would want highlighted for every part of the if blocks, even the parts that aren't actually involved in that particular compiler, in
yeah,
that particular pass. And so, it's like it's a different problem, and particularly ill suited to something like a parser generator, because you're trying to do sort of like intuitive stuff. It's more like
yes,
Chat GPT than it
yes,
is like Yak, right? And
yeah.
so, you know,
Heuristics are going to be involved no matter
yeah.
what, and you want to make it as easy to do heuristics as you can. Actually, this is reminding me of all things, the gameplay code engine for the Sokoban game, actually,
Okay.
because it's like, if you can do the strict core rule set and it works and you're not seeing any problems, then absolutely do that. And because you want to be correct, right? You don't want to be engaging heuristics on something that parses correctly, right? But as soon as you hit something that doesn't parse correctly, it's like, okay, you want the heuristics to kind of plug in and take over and be like, oh, this looks like we were maybe going to do this construct, but it didn't. Some piece of punctuation is missing or something, right?
Yep.
And um, obviously, that the thing about those heuristics is they never end. Like you can make a better and better user experience by layering more and more of them. Maybe at some point you go way too far, like Microsoft with trying to type into Visual Studio and nobody wants to use it anymore. But if you're at, that's just making good versus bad decisions, right? But that's actually what the Sokoban game engine works like. Is like, look, there's this strict stuff that has to happen to maintain the integrity of the moves, but for better game feel, we can plug in little rule exceptions that are allowed to like let things happen and then clean up the result. It's a little bit of a different thing, but it reminds me of the same thing. And but It's a little bit different because in the Sokoban case, we have to be correct in the end, no matter what. Like there is a correct answer, whereas
Where syntax
in the
highlighting
text
it's not
editing,
so
it's
bad.
like, yeah, I don't know. It's yeah. Did this rewrite speed up slightly the compiler? I haven't noticed, but probably not. Like again, the parser is pretty fast. Um, it's all the later parts of compilation that are slow. I did say 10% was getting memory, but we still need to get the same amount of memory. Like we haven't changed the tree representation or whatever here, right? So the actual code that runs in the compiler is very fast compared to the stuff that type checks. Like type checking is our entire bottleneck. Type checking is the hardest, most see, I can't even speak anymore. There's no blood to the brain. Most rat's nesty part of the compiler. So yeah, any changes, the only way that I anticipate a speed difference is if somebody puts really dumb stuff into the parser and slows it way down. But you're not really going to see speed ups from that. Do you tokenize the whole thing all at once or as the parser asks for tokens? I do it as you ask for tokens, which may or may not be good. Again, it might be faster. So the thing is, because your tokens have a clear, this is not true in C. You could probably make it true a little bit in C. We talked about this last time about how parsing doesn't have to be the final word in what things are. You could like reinterpret them later by changing the tree around. So in C, the classic thing is it does matter that something's a name of a type. That's not the same thing as a variable name. And there's stuff that you wouldn't be able to parse if you didn't know what all the names of the types are in C. So there you can't strictly generate tokens ahead of time without parsing if you have a token for name of a type and a different token, right, for a different thing. But you could have a token that just says, this looks like an identifier. Maybe it's a variable, maybe it's a type name, I don't know. And then there's some if statements that run when you see that, right? And that's when, but that could be generated by the lexer ahead of time because it doesn't need to know the types, right? The point being, you could have, if you were in a very parallelism mindset, you could just have one thread just blast through the source file, generate all the tokens for the source file, and those are just sitting there linearly in memory, right? You could use just, virtual alloc or whatever to just put the tokens next to each other, and they're just like all there. That would be much bigger than the source file, but source files don't tend to be that big. And then you could have the parser just read linearly those tokens. I don't do that because, I don't, again, it's not a speed problem. And it just, someday, if that ever comes up as anywhere in the top 500 issues with the compiler, I could think about it, right?
That also doesn't sound faster.
Right.
It sounds slower, what you just described.
I mean, it's sort of like you are jumping around between different code, and maybe the lexer has its own data structures, and maybe the parser does. So you're touching different pieces of memory, but modern CPUs and modern caches, like it's not like parsing is that complicated. It's not like lexing is that complicated. Modern CPUs are going to be able to hold all that easily. I would say, not having done the performance analysis, my guess is that it's all fine and it doesn't matter. And that's why I didn't really think seriously about it. It's just fun to think about though. Like, oh yeah, I could just really have a tight thing that just cranks. And in fact, I could split the source file up at new line boundaries into multiple and have multiple threads generate this long series of tokens in parallel and just really up the token rate. And you would literally never notice this in the resulting speed of the compiler because, well, A, as Casey said, it may not actually be faster.
I don't think it would be faster. Yeah.
But B, it's negligible in terms of the time spent by the compiler anyway. Don't make things more complicated than they have to be. Someone's asking again, is it faster? It doesn't matter. Someone says, I like grammar specifications since you can then use a parser generator and you are good to go. Cool story, bro. I think you have a definition of good to go that is very different from my definition of good to go.
Maybe as long as good to go means you're good to go, rewrite it as something better.
You're good to go. Get a job at McDonald's.
Oh God. Okay.
Okay. Um, Not that there's anything wrong with having a job at McDonald's. Okay?
You're good to go work somewhere else, is I guess what you're saying.
Yes.
Yeah.
You've shown your token structure in the original parser's video. What is the atom star? Is that a string? That's basically, it was a way of interning the strings on the Lexer side so that you don't have as many strings that you're allocating and stuff. I don't have a separate structure for that anymore. Sometimes I make decisions for clarity and then later I'm like, oh, that actually wasn't confusing, right? So, we have a char star for like, what is the name of this thing? And that gets interned locally to the Lexer. Now, there can be multiple threads parsing stuff because we just load up a bunch of files and parse them simultaneously. And so interned for that so the parser and the Lexer are like bundled, although they're essentially the same thing as far as anyone should be concerned. And so there's essentially a local cache of what all the strings are for there, but you don't want to like synchronize that with other threads because that just seems like a lose. So they're like kind of interned. And is that a good idea? Maybe not anymore. Like it used to be that things were globally interned. And what that meant was, like when you're comparing identifiers, if you want to know that this is the declaration of this identifier, you just check if the string pointer is the same, right? And that's what that atom struct was. That like, sort of wrapped that to make it clear that that's what was going on. But once I went to a more parallel design for the parsers, it's like, is that really worth rescuing? Probably not, because you don't like do that many string compares. And large namespaces are in a hash table anyway, and you have a hash table for the identifier, and you can compare that to see if it's the same. So there's not really much like the complexity you would lose in making threads synchronize with each other to make sure they had the right canonical version of an identifier is like, that's just way worse than whatever the gain would be, I think. But again, we have literally never been hardcore about making this compiler go fast. It's like there have been a few times, a couple years apart each, where I spent a couple days doing some stuff to make it faster. And, you can compare the speed that you see to something like GCC or Clang and decide what you think of it. But it's just to say that we could have much greater levels of speed if we actually did that. Like we haven't designed for speed. I don't even know. It's been complicated enough to solve the fundamental problem of just implementing the semantics of this language that I know I'm designing for not pathologically dumb and slow, but we're not designed for fast yet. That I hopefully will come later. Someday. Someday not too long in the future. I'm going to believe. Could you give us your thoughts about IR if it's a valid thing and generate bytecode? Yeah, we generate bytecode. I think that's the main. So you have to kind of understand what is the job of that, right? And it'll make sense if you understand what it's for. So if you want a compiler that lets you compile your code for multiple CPUs or even, let's just say multiple CPUs, keep it simple. And the CPUs are very different from each other. And they have different instructions that don't necessarily have analogs of each other sometimes. And you also don't want to have to completely rewrite your whole compiler next time there's a new CPU. There's not been a lot of CPU innovation lately. It's all incremental, but maybe someday, once AIs are all designing CPUs instead of people, we'll actually make some progress again, right?
Except the AIs are all example based. So
yeah, they'll just remake.
They'll just be redone versions of the existing CPUs.
They'll make AMD 64 instruction set, except there's 3 more padding bytes on the front that like tell you different things. Yeah. So So what the bytecode is for is to let you do instruction-based code generation, which is very important. Like, your computer actually runs instructions that you could sort of write them out one per line, and they're relatively simple compared to a higher level program. And like that's just the way the CPU operates. And so the job of the compiler is in some sense to bridge the gap between text that some dude wrote, right? And then that list of instructions that the CPU understands. And the steps that we've been talking about so far are mostly about, so first of all, parsing, getting that tree representation. What is the tree? The tree is a representation of what has to happen when, but it's not that linear. You have to like do a walk on it, and you probably have to do, once you look up the identifiers and figure out what the function overloadings are and whatever happens, you end up with a result later that's like more like the semantic version of the tree, right? The semantic version of the tree has all these blocks and stuff, but not the basic blocks we were talking about, but like blocks of instructions. And then you have to go somehow from here's an array of instructions that are still represented as tree nodes to like something more like instructions from a CPU. And then you could do that separately per CPU. You could say, okay, here's my backend that walks the tree and generates code for x86. Here's one that does it for ARM. And the problem with that is that you will end up with way too much of the compiler duplicated between all those. And it'll just be a huge mess because it's just an interesting situation where there are quite a few optimizations that you want to do with a particular CPU in mind. But there are really most optimizations that you want to do are not even particular to a CPU. It's just like, hey, I realized that inside this scope, I define this variable once and then nobody else can write to it. And that means a lot of things in terms of, what instructions we would generate. And that's invariant to whatever the CPU is that's running the code. And so that kind of optimization you want to happen. You want to write that once, hopefully, in as simple a way as possible, because there's going to be actually a large number of these, right? And all the things we alluded to before, like a data flow graph or control flow graph or whatever, are used to figure out these things. Like, what can we rely on that's true so that we can be smarter about generating code? Because what makes code dumb and bloated is like, if you can't be sure about something, right? So the C keyword restrict is like a Band-Aid. I don't mean that too pejoratively because it's like, I'm not sure what else you would do in that situation, but it's a way of saying like, look, you can assume certain things about this pointer. So, if you're reading some other value, you don't have to assume, for example, that a write through this pointer changed this other seemingly unrelated value. If it seems to be unrelated, it really is unrelated. So you don't have to keep reloading it all the time and whatever to make sure. All that kind of stuff, the CPU doesn't matter, right? And so you want to implement it and debug it and make it work well, right? And then, so that shouldn't stop you from doing CPU specific optimizations, but those happen in like the actual backend, right? But the bytecode instructions get you a substantial amount of the distance from the semantic tree to the actual instructions on the CPU, right? And then it's much easier to say, oh, I have like a bytecode for some fictitious virtual machine of my own. That's an array of instructions with my own, the way it's implemented is there's a program counter or whatever, and it's just running, in an interpreter essentially. Mapping from that to instructions on a CPU is a much closer mapping. And so then you can get away with having a lot less code than you would otherwise, right? How do you organize identifiers in the scope hierarchy? It's really stupid. I don't. It's not good. We'll put it that way. How to make a good optimizing compiler? I mean, that's the hard part. So, earlier I kept saying parsing is the easy part. other things are hard. Really, the only hard thing in compilers is optimization. Well, and proving your program is correct, which is basically impossible right now. Those are the things that are hard. Like all the other stuff is easy. I mean, maybe like design is an art. So you could say designing the right thing is hard. But in terms of actually what you type, actually it's sort of a lie. The other thing that's hard is just if your feature set is really ambitious, as ours is, you just end up with this kind of car crash in the middle of the intersection where all sorts of stuff is happening all the time. And like part of the beauty of a programming language is like all these things are just expressions, right? And they interact with each other, and you have these features that you can use on the expressions in your language or whatever. And the more features that you give people, the more that they have to work all the time in concert with each other. And that generates a kind of an n squared explosion of potential problems. That's actually the other hard thing besides optimization is just, but that's the same thing as in other programs. That's the same thing as in video games, right? It's just like at some point, what we're trying to do is really complicated, and it becomes difficult to understand even what we're doing and how to do it well. And that's always, especially these days, why I'm very concerned with simplifying things all the time, because I've just suffered through too much of like, oh, all these things are way more complicated than they need to be. It's causing problems, but bad problems and then really bad problems, right? So bad problems are like, oh, it's taking 30%, 50% longer because of all this friction, 90% longer. Those are bad. You might run out of money or get depressed and never finish your project. But the worst problem is, like, I have in my brain some maximum ability to visualize something that I could work on, right? And like, if I could somehow go to the gym and work that out, and make it better, which I think is what programming does. Like, I'm not claiming this is fixed, but it probably slowly grows over time. Although someday maybe I'm getting old and it'll shrink, but I feel like it's still growing. So what I can even, ignoring the friction component, what I could even ever accomplish is kind of bounded by my ability to harness a complex situation and deal with it mentally, right? And so there's only a certain amount of space in there. And if you take up a bunch of that space with stupid stuff being a lot more complicated than it needs to be, there's less space for other stuff. And so the total functionality that you're able to do is smaller, right? Because you just wasted a bunch of it. And I don't think people take that very seriously. And I think because, well, it's in a different guise, right? Because I've done a lot of stuff where I'm the main programmer, I see that very directly, right? When you have a company like, Google or someone, Twitter, old Twitter especially,
bang,
it doesn't fail in the same way. What happens is you actually hire more and more people, and then those people know less, and the quality of the product starts just sliding downhill because there's like, making complex software work well is a coordination problem. Like, there's all these issues that need to be handled, and there need to be things that handle them, and those wires need to be like all hooked up, and that can get very complicated. And at some point, if there's a lot of people with small enough responsibility, those people can't see this well enough, and so they just do their local area of it, and it screws up other things, and just nobody even like sees the perspective that would have avoided that. And so I don't know. I think that's the number one problem in software, actually. And LLMs, someone's going to say LLMs don't actually understand anything currently, so they can't help you with that. Maybe someday we will solve AI and it'll help you, but right now it doesn't. All right. I feel like we've been going a long time. It's been 2 hours. No, 3 hours.
3 hours, I think. Yeah.
Dude, we're cutting into my video game playing time.
Here's the thing, though, John, is I have seen you your stream being titled or saying that you are going to escape from Tarkov, and you clearly have not escaped, because if you're still there, if you're still playing, I mean, what's the explanation?
Well, you see,
you must be really lousy at this video game if you can't escape after this many hours.
You just have to
and
keep
the only
trying.
thing the game is called is Escape from Tarkov.
Yeah, well, it's like slaying the complexity of compiler design with Layler, parser generator, and syntax directed translation. If it didn't work the first time, you just got to keep swinging that Layler, parser generator sword. Yep. One of those times, it'll work.
Yep.
All right, thank you, everybody. I do have to say, some of my answers were not that good, especially in the latter half. So I regret this, but at the same time, this is just what we're able to do. Like, this is not my job, and I have all this stuff I have to do. And I do want to someday write a compiler book, because I think it would be different from everybody else's, and I think it would be a good contribution. And that will be much more premeditated.
And the cover will be awesome. The cover will be amazing.
I don't know what it'll be, but it'll be amazing.
That's right.
Yeah. All right. But thanks for coming by. And so what I would like to end with an exhortation of, please, for this entire class of things. So again, to review for people who weren't here, the entire point of this was how actually simple this parsing precedence thing is, that not everybody, but most people have made a big deal out of, and how difficult it is to find the right information. And culturally, we need to recognize that this is a problem. Like, a lot of things are actually pretty simple, and for some reason, we're not doing a good job of understanding those things collectively as like everybody. And so one thing to do is, when you find something like this that's actually simple. Now, you don't want to be a bozo and claim something is really simple when it's not, because some things are complicated. But when things are really simple, just helping to signal boost the fact that they're simple and they don't require you to get a degree in, parsing science or whatever to know that times goes before plus. Like, it's just not how it is. But you would think it was, and a lot of people who got computer science degrees think that's how it is. But the point is, there's many things like this, and if you could pitch in and let people know when things are simple, that's great. And it's fun to do. That's the thing. I mean, Casey could probably vouch for this, because you do a lot more of this now these days than me, of just like explaining stuff to people. It's like finding a good explanation that's as simple as you could make it, and making sure you really understand it, and then presenting it. Even though, I mean, again, I went through an Emacs file with like some trees as like slashes. So it's not like I wrote a book again, but like, it's an enjoyable process, and you understand it better at the end, but then you feel good because it's like, look, I gave people this thing, right? And so we need more of that, and less of like, I'm writing this thing to show everybody I'm smart. That's what I would say.
Yeah. Also, I guess one problem that we have as well. So I mean, not to keep this discussion going any longer, since it's been too long already, but I think it's harder than your exhortation makes it out to be, though, because, like, I mean, we literally just had a thing on Twitter where someone was like, I figured out how to check if a point's in a polygon, and it was like the worst algorithm I've literally ever seen for that.
But that guy was like, not really a programmer, right?
Or whatever, right? Yeah. And it's just, the problem is that knowing when something is simple and easier to understand is itself a very hard thing to do. And most people can't do it. They think they have found a good explanation, and it's awful. Like, I don't think the people who wrote the Dragon book think that their explanations are awful, but they are, right? And so I don't know, like, the problem is harder than your
No, I agree with that, but I think,
and I don't know what the solution is. I don't know if there is a solution.
I think there is incremental improvement that can be made that causes feedback that accelerates the improvement. So the problem is really that the culture is broken, right? And it's broken for a lot of reasons. This is merely one of the lobes of brokenness
Okay.
of what's happening, right? But it's a major one, really. And like, if we kind of had a no bullshit culture in programming, which there used to be, like, I caught the tail end of that in college, right? It was still kind of gone by the time I was there, but nowadays it's the opposite. It's like programming is like full bullshit fire hose culture, right? It's like somehow inverted, and it doesn't have to require being blunt or mean, but just like having a low tolerance for nonsense, or having a low tolerance. Well, here's the thing. How does something like the Dragon Book propagate? It's like, well, a lot of things have to go wrong. It's like, first of all, the better explanations have to be ignored, right? Somehow. And then people have to think that this is actually a good enough explanation that doesn't require improvement over the decades that it's been used, right? And how do they think that? Do they read the explanation and think they understand it, right? I mean, I would claim, like, there are different levels of understanding, but I would claim ultimately that the answer has to be no, because if you look at all this complexity that you're building in order to do this simple thing, it's like, but wait, I know what I can that was the realization I had in college after doing like 5 languages or something, was like, wait, I know what I could program, and I know what this thing is producing, and it's worse than what I could program. That's some kind of synthesis that happens, right? That synthesis is broken for everything almost. So we need to get that back. I don't know, like, maybe this is too rambling, but there's just issues. Like, maybe, and again, we've talked about this before, but maybe the fundamental issue is that the culture of programming needs to be built around acknowledgement of clearly demonstrated quality, right? Because like, if you had an MMA cage match between Layler parser generator and like hand coded thing, like the hand coded thing would win on every metric, actually, right? Like, literally, it would win on speed, it would win on time to successfully create the thing, it would win on
it would lose on
debuggability,
one thing,
ability to publish papers.
no,
Yeah.
it would lose on incremental. So it's very hard actually to write an incremental top-down parser that can stop at any point. It's harder.
Yeah.
LALR
Okay.
just already does. It's like it is that by design. Like, you just get that for free. So
Yeah.
that's the one thing I can think of. It's like top down. It's much harder to write a top down stop anywhere parser that can just like take a new token arbitrarily as like an input generally, without having to because it uses the program stack. I mean, that's just kind of how that is.
Yeah,
Right?
I see the point. I will just say that because I haven't thought about the problem, I'm not sure that it's actually all that hard. Simply because, like, that's easier than the frickin' type checking stuff that we do, which has to stop anywhere. So, you know,
I'm just saying it's not. It's easier in LAR because it already works that
yeah.
way.
Well,
Right?
let's put it
Like,
this way.
it has a state table, so
Oh,
it's done. It doesn't
yeah,
have to do anything. Right?
You would have to add, like, the code that we showed today would not do that.
Would not work. Yeah,
Yeah.
you have to add stuff to it. Is my only point. But anyway, keep going.
Um, but it may not even be that much. But the point being, like, that's just not the culture somehow. And the culture is just, you make claims and then people believe the claims, and the claims act as propaganda, and that's how everything gets popular. And it's just really harmful. And I don't know. At this point, it's nothing I haven't said before, but the end.
All right.
All right.
And
Thanks,
everybody.
Casey, for coming by and talking about this for several hours.
Oh, no problem.
I
Thanks for
didn't
the
know it was going to
explanations.
go
I
this
think they were
long.
good. No, but I like the like, as someone who does not work on parsers, I appreciate new explanations of them, because if I ever actually do decide to go write a parser, this I am almost certainly in a much better position.
Well,
these
I
days
could
than I would've
recommend
been
you a
before.
book right here.
Yeah.
It's got excellent
All right.
computer graphics.
Yes. Yes.
Yeah. All right. Thanks everybody for coming by. We'll post this on YouTube later because you surely missed a lot of it because it's 3 hours.
Yep.
Thanks.
Take it easy, everyone.
Yeah.